శనగపిండితో అనుకున్నాను అవ్వటం లేదు. శనగపిండిలో
Good morning, sir. Good morning. Good morning, sir. Good morning.
Participants, please mute your audio and video.
Dear organizers, please enable the chart. Dear organizers, please enable the chart.
Okay.
నవీన్ బయట ఒకసారి అక్కడ వెళ్ళు, అక్కడ ఏమైనా అవసరం ఉంటుందా? వెబినార్ మొదలు పెట్టుతున్నారు కదా, వెళ్ళి ఒకసారి. ఇప్పుడు అది కొంచెం టైం పడుతుంది. ఎక్కడికి చేసాము, అందులో కరెక్షన్స్ చెప్పారంట. అది అన్ని కరెక్షన్స్ చెప్పాలి, అది కష్టపడ్డప్పుడు. చెప్పండి.
అంటే చూడు. ఎంబోయి ఒకటి ఉంటే మనం హలో దివాకరు, హలో
హలో హలో గుడ్ మార్నింగ్.
కిషోర్ మాట్లాడు. గుడ్ మార్నింగ్
సార్ చెప్పండి సార్.
ఎవరు కిషోరా?
అవును సార్, కిషోర్ మాట్లాడుతున్నాను. చెప్పండి సార్.
ఏంటి స్టార్ట్ చేయండి, టైం అయిందిగా.
అదే సార్, ఒక నిమిషం.
పార్టిసిపేట్ అయితే 76 ఉన్నారు కదా
సార్,
పార్టిసిపెంట్స్ 77 ఎంతమంది ఉన్నారు కదా.
77 కాదు సార్, 264 వచ్చారు సార్.
ఓకే ఓకే, మరి ఏంటి ఎవరి కోసం వెయిటింగ్?
అంటే సార్ చెప్పాలి కదా సార్.
హలో దివాకరు,
కిషోర్ మాట్లాడుతున్నా, చెప్పండి సార్.
కాదు కాదు, ఏ జగన్ ఉన్నాడా?
ఉన్నారు సార్, ఉన్నారు.
ఏంటి ఒకసారి
స్టార్ట్ చేస్తున్నా సార్.
కరస్పాండ్ గారి దగ్గర పంపారు ఎవరినన్నా?
సెక్రటరీ గారు లేరండి.
మొత్తం ఇట్లా అన్ని కాలేజీలు
జగన్ హలో
అదే వాళ్ళు మ్యూట్ పెట్టుకోకపోతే అలా
హలో
హలో సార్, చెప్పండి సార్.
కాదు, సెక్రటరీ గారి దగ్గరికి కరస్పాండెంట్ గారి దగ్గరికి పంపారండి?
పంపించాను సార్.
వాళ్ళు ఉన్నారు, లైన్ లో ఉన్నారా?
సెక్రటరీ గారు లైన్ లోనే ఉన్నారు సార్, ఇంకా కరస్పాండెంట్ గారు రాలేదు సార్.
మరి మొదట టైం సరిపోదు కదా మళ్ళీ మనకి.
సెక్రటరీ గారు జాయిన్ అయ్యారు సార్. సెక్రటరీ గారు జాయిన్ అయ్యారు.
కరస్పాండెంట్ గారు వెళ్ళారు కదా ఎవరన్నా ఇక్కడి నుంచి?
వెళ్ళారు సార్.
ఒకసారి ఫోన్ చేయండి.
ఓకే సార్, ఓకే. కరస్పాండెంట్ గారు
స్టార్ట్ చేసేయమ్మా, తర్వాత చూద్దాం, మధ్యలో పెడదాం.
సార్ కనెక్ట్ చేయండి. రెడీ అయిపోయింది. ముందు ఆయన కాదు మేడం అడ్రస్ చేస్తారు, తర్వాత సార్. ఓకేనా? ఓకే ఓకే, ఇచ్చేసారు సార్కి.
Good morning to everyone. It gives me immense pleasure to welcome you all this bright morning to the national webinar on mathematical applications on differential equation. I extend my warm welcome to distinguished guests and all the participants. I express my gratitude to the Department of Mathematics for organizing this webinar in this critical time of pandemic COVID-19. A good beginning is work half done. As such, I would like to begin with a short introduction of our prestigious institution with the help of small AV coming down to you. Can I have the AV, please?
సేఫ్ డ్రైవింగ్ మోడ్ అట.
కిషోర్ కిషోర్ హలో
కనెక్ట్ కనెక్ట్ అయింది ఇక్కడ టెక్నికల్ ప్రాబ్లమ్స్ చూసావా 5 minutes ఇక్కడ టెక్నికల్ ప్రాబ్లమ్స్
A good begin is work of done. As such, I would like to begin with a short introduction of our prestigious institution with the help of small AV coming down to you. Can I have a heavy, please? Next. ఇక్కడ ఏవి రావటం. Now, continuation ఏవి నాకు కనిపించలేదు. The Honorable Sri Kumar, President of our CRR Educational Institute, Dr. MBSV Prasad, Secretary of our institutions, Dr. K. Vishmohan Garu, Correspondent, Dr. K. Ramaraj Garu, Principal, Dr. K. A. Emmanuel, Vice Principal, form the backbone of our institution, under whose blessings and guidance we all are able to flourish. It's because of their support and encouragement that we are doing this innovative activity today. Now prayer. In this innovative activity today.
Shubham kurutvam kalyanam arogyam dhana sampada. Shubham kurutvam kalyanam arogyam dhana sampada. Shatrubhutinashaya dipajyotirnamostute. Shubham kalyanam arogyam dhana sampada. Shubham kurutvam kalyanam arogyam dhana sampada. Kalyanam
Now I request our principal sir, chairperson of today's webinar, Dr. K. Ramaraju Garu, to kindly grace the webinar. I take a privilege to inviting Dr. MBSV Prasad Garu, Secretary, Sir CRR Institutions, kindly join to the webinar. Now I request to Dr. K. Vishnu Mohan Garu, correspondent of our college, kindly join webinar. I would like to invite Dr. K. Emmanuel, Vice Principal of our college, Dr. MBSV Prasad Garu, request Dr. C. Jagan Mohan Garu, kindly join to the webinar on the platform. Now I request to Dr. K. Vishnu Mohan Garu, correspondent of our college, G.P. Rajshekar Garu, Professor, Dean, Planning and Coordinator of IIT Kargapur. And also I request to invite Dr. Vamsi Krishna, Assistant Professor, Greatham University, Hyderabad. Thank you, sir, for being with us. Now, now introduction to the webinar by Dr. B. Jagan Mohan Garu.
Welcome everyone. Thank you for joining for us today's webinar. My name is Dr. P. Jagan Mohan Rao, HOD, Department of Mathematics. Sir, CRL College is one of the prestigious educational institutions in state of Andhra Pradesh. Was established in 1945 in Eluru, the district headquarters of West Godavari. The college was named after the founder, Vice Chancellor of Andhra University, and its educationalist, Sir Kattamachi Ramalinga Reddy. Mathematics department in our college, established 1945. Presently, we are offering the mathematics to 630 UG and 40 PG students. Presently, 16 teaching staff members are working in the department. At present, 7 mathematics combination courses are offered and affiliated to Adhikavi Rannaya University, Rajahmundry. There are BSc, MPC, MPG, MPCS, MECS, MS, MCCS, MGCS, MSCS. So our department organized the today national seminar on emerging trends on mathematics with 23 conference research papers submitted by the participants. So and other our department organized the 1 week national workshop, quality improvement in higher education by the department. Recently, our department is conducted. Recently, we have organized the International Conference Industrial Application of Mathematics and Computer Science during February 2020 with the conference research papers submitted by the participants. The department also conducted value-added course on MATLAB. Today we are conducting the national webinar on mathematics application on differential equation. The resource persons are Dr. G.P. Rajshekar, Professor, Department of Mathematics, and also Dean and Planning and Coordination, IIT Kanpur. Dr. N. Vamsi Krishna, Assistant Professor, Department of Mathematics, Greatham University, Hyderabad. I am very thankful to Dr. MBSV Prasad Garu, Secretary of the CRL Education Institution, Dr. K. Vishnu Mohan Garu, correspondent of our college, Dr. K. Ramaraju Garu, principal of our college, for the cooperating us to conduct the webinar with this short period time. In this webinar, an attempt is made to understand few applications, ordinary differential equations and partial differential equations, and apply them to research studies. Thank you, everyone.
Thank you, sir. Now, the opening remarks by Secretary Sir, Dr. MBSV Prasad Garu.
Am I audible?
Yes, sir.
Good morning, everybody. And today is a very important day. and we are organizing CRD College or PG and UG departments are organizing mathematical applications on differential equations. And mathematics is an important. India is one of the fast developing countries in the world. Our country still needs a lot of development in the fields of science and technology. A lot of research is to be done in these fields. The government of India is encouraging research in all new means, webinars, and use of online tools are the need of the hour as well. All to know that there is no science and technology without mathematics. And at this juncture, we have to remember our great Indian mathematician, Srinivasa Ramanujam, who was a world famous in those days. Still, his theories are very much applicable and proud to know. And India is one of the country who detected zero in the mathematics. Maybe so many other countries claim that they are the people who detected, but India is the first country, as per the history or for the records, zero. The importance of zero in mathematics, everybody knows. And I convey my wishes to resource persons, Dr. G.P. Rajsekar, Professor IIT Kharagpur, Dr. N. Vamsi Krishna, Assistant Professor of Geetham University, Hyderabad, for accepting our invitation and sharing innovative knowledge through virtual platform like Zoom. I am sure that this webinar on mathematical applications on differential equations would provide an exposure and expertise for senior researchers and to students and a scope to choose a career in mathematics during the forthcoming years. I congratulate the faculty of the departments of mathematics, especially UG and PG, and Dr. B. Jaganmohan Rao Garu, HOD, and Dr. Sri P.N.V.S. Prasad Rao, and Srimati Hemalata, the organizing committee for conducting such a innovative academic activities. I wish the webinar a grand success. I thank you everybody for giving me this opportunity to address you. Thank you very much.
Thank you, sir. Thank you very much for giving your valuable speech. Now, I invite Principal sir to give you your valuable message.
Thank you, Hemalata madam. Respected Secretaries RCRD Group of Institutions, Dr. MBSC Prasad Garu. Respected Correspondents RCRD Autonomous College, Dr. K.S. Vishmohan Garu. Respected Vice Principal of the College, Dr. K. Emmanuel Garu. Respected Head of the Department of UG Mathematics, Dr. B. Jaganmohan Rao Garu, and other members of the organizing committee, important resource persons, and the participants, a very good morning to all of you. I take it a great privilege to be among with you in this one-day international webinar on mathematical applications on differential equations. Without mathematics, there is no stable path to say for physics, chemistry, medicine, history, and economics. Mathematics is the life breath of all academics. It gives me an immense pleasure to learn that our college Department of Mathematics, both UG and PG, is organizing a one-day national webinar on mathematical applications on differential equations. Present days, it is well known that a good knowledge of mathematical tools is very essential to understand and update themselves during COVID-19 lockdown period. It also gives an opportunity for participants to interact, deliberate, and debate on differential equations of mathematics and technology. I thank the resource persons, Professor IIT Kharagpur, Dr. N. Vamsi Krishna Garu, Assistant Professor Geetham University Hyderabad, for accepting our invitation to share their valuable knowledge. In this context, I congratulate the organizers of the Department of Mathematics, particularly Head of the Department of Mathematics, Dr. B. Jaganmohan Rao Garu, Dr. PNV Prasad Rao Garu, Srimati Hamalata Garu, and other members of the Mathematics Department for conducting this webinar, as it builds a platform for young minds and researchers to share their ideas and views. I also thank our management for giving an opportunity to our college to organizing these type of webinars and seminars. I thank you very much for all of you for giving me this opportunity, and I wish the webinar will be a grand success. Thank you one and all. Hamalata Garu. Kishore.
Thank you, sir. Thank you very much for your valuable message. Now I invite the Vice Principal of our college, Dr. K. Emmanuel Garu, sir. Give me your valuable message.
Hello. Hello.
Sir.
Am I audible to you?
Yes, sir. Yes, sir.
Is it my program? Just now I lost my current in my house. Therefore, I could not join you. Now I am joining through my mobile phone. Shall I continue?
Yes, sir.
Okay. So, Honorable Chief Guest, respected Principal, and respected Correspondent Garu, respected members of Organizing Committee, dear staff, ladies and gentlemen, it gives me immense pleasure to extend a very warm welcome to all of you present here on behalf of Sir C.R. Reddy College. First of all, I compliment the Department of Mathematics, both UG and PG courses for organizing on mathematical application on differential equations. It is gratifying to note that the agenda of the webinar covers a wide range of very interesting items relating to the mathematical application and differential equations. The study of differential equations is a wide field in pure and applied mathematics, physics, and engineering. Many fundamental laws of physics and chemistry can be formulated as differential equations. In biology and economics, differential equations are used to model the behavior of complex systems. I once again compliment all those who have been associated with the organization of this highly creative webinar. I wish you, all of you, all the very best in your professional lives. Thank you very much.
Thank you, sir, for giving your valuable message. Now, introduction of chief guest by N. Anu.
Respected dignitaries and all the participants, good morning to one and all. Am I audible, sir?
Yes, yes.
Hello. Yes, sir. Good morning, sir. Respected dignitaries and all the participants, good morning to one and all. It is a great privilege to introduce today's resource person, Dr. G.P. Rajshekhar Garu. Sir did his bachelor degree from Andhra University in the year 1990 and master's degree in applied mathematics from University of Hyderabad in 1992. MPhil degree in Applied Mathematics and Fluid Mechanics from University of Hyderabad in 1993. Sir completed his PhD in Applied Mathematics on the paper Fluid Mechanics from University of Hyderabad in 1997. Currently, his main area of research is on biphasic mixture theory, deformal porous media, thermocapillary migration of viscous drops, modeling flow through antistropic porous media and multiphase flows. And also specialization papers are PDE theory and applications, fluid mechanics, and boundary integral methods. At present, Sir working as a professor on HAG scale in Department of Mathematics and also working as Dean for Planning and Coordination IIT Kharagpur 2019. Previous post held in past are from January 2009, January 1997 to November 1998. Sir worked as a guest faculty in Department of Mathematics and Statistics at University of Hyderabad. From November 1998 to December 2000, Sir worked as a JSPS postdoctoral fellow in Department of Physics, Tokyo University of Agriculture and Technologies, Japan. From December 2002, August 2019, Sir worked in various designations like visiting faculty, assistant professor, and associate professor in Department of Mathematics, IIT Kharagpur. From January 2009 to December 2009, Sir is on sabbatical leave for Institute of Applied Analysis and Numerical Simultaneous University of Stuttgart, Germany on Alexander von Humboldt Fellowship for Experienced Researchers. Under the guidance of Dr. G.P. Rajshekhar Garu, 9 students got PhD and 5 students are ongoing PhDs. Sir's publications are around 87 papers are published in national and international journals. Sir qualified GATE with 95% in 1993. From 1992 to 1994, Sir worked as Junior Research Fellow, and from 1994 to 1997, Sir worked as Senior Research Fellow of CSIR UGC. Sir won Japan Society Fellowship from 1998 to 2000. Sir won Young Scientist Award in Mathematical Sciences given by Indian National Science Academy in the year 2002. Sir got visiting opportunity of Royal Society, Indian National Science Academy in 2004. From 2008 to 2010, Sir got Alexander von Humboldt Fellowship for Expert Research by Alexander von Humboldt Foundation, Germany. Sir got citation for Bhatnagar Memorial Award Lecture, Indian Mathematical Society in 2016. Sir got Fellowship of Andhra Pradesh Academy of Sciences, Amravati in 2017. Sir won Mathematician of the Year Award by the National Institute of Technology, Warangal in 2018. Sir got JBS Gold Medal by Indian Academy of Mathematical Modeling and Simulation, IIT Kanpur, India. Sir visited 13 countries over the world. Sir doing 5 major research projects from 2017 to 2022. Sir also sponsored NEPTAL courses. They are modeling transport phenomena of microparticles and numerical solutions of partial differential equations and ordinary differential equations. Friends, we are very fortunate to have such an eminent person in our midst. Thank you one and all for giving me this opportunity. Thank you, sir.
Thank you, Anu. Now I invite today's chief guest, Dr. G.P. Rajshekhar Garu, to give your invited talk.
Okay. Good morning to the entire management of Sir C.R. Reddy College. So may I know it is audible?
Yes, yes.
Yes, sir.
So good morning to one and all. And I indicated to our friends not to have such elaborate formality introducing me elaborately, but anyway, I could not avoid. So I thank the management and the principal for inviting me to this webinar. And I see a large list of participants. The timeline between the announcement of this webinar And today's date is little short, but nonetheless, I will try my best to justify the title. Okay, so the title is about differential equations and applications. So my talk contains about two parts. Part one indicates about basic methods, etc. And then part two contains some application. So my humble appeal to all the participants is to kindly keep your microphone on mute all the time, unless you have a question. Okay. So hope you understand, and then kindly implement the same. So
Okay, uncle.
hello, hello. Am I audible?
Yes, sir. You're audible, sir. Now.
Yeah, sorry for the inconvenience, some technical issue. So let me share the screen.
Sir, audible, sir.
Yeah, I'm just yeah. So may I know whether the screen is visible?
Visible, sir.
The screen is visible?
Visible, sir.
Okay, so yeah. So welcome back. So as I indicated, the title is on PD and applications. So the first part, I will touch a little bit on analytical, semi-analytical methods to solve PDs basically. Yeah, when you say differential equation applications, so ODEs also have potential applications, but I'll proceed with PDEs, maybe a little bit on ODE. Okay. So the credit is two parts. First part is these are my PhD students, and second part is a specialized work on some of the research that we are doing. So this I would like to credit to my students. So now, what is human tendency? Human tendency is, given a differential equation, we simply try to solve. Okay, so this is very, very often I see with various colleagues when I interact, especially youngsters. What they do is they see an equation and then try to solve. So that is analytical expertise, because they know some analytical methods. On the other hand, suppose somebody is a numerical expert, what they would do is they try to discretize the equation and obtain the corresponding system and then try to invert the system solution, right? So this is a numerical expert, and little bit true mathematician in some sense. First they will wait and watch. Okay, I'm getting a lot of echo feedback. My request to put off the microphone. Yeah, so the mathematician wait and watch, but how long? Certainly not forever, until the following are asked. So what are the following? Look at the equation and ask the following. First thing is exists. What do you mean by exists? Whether the solution exists for this problem, if it is time dependent or a parameter dependent. Okay, t could be any parameter. Whether a solution exists for all t greater than 0, so then the solution is global. If solution exists within an interval, then it is a finite time solution. Okay. So after this, what is the next question? If solution exists, whether the solution is unique. So this is another important question to be asked. Okay. So first thing is existence. Second thing is whether the solution is unique. Then what is the next? Suppose you are getting a solution which exists and unique. So then if you disturb the boundary data a little bit, whether the solution is blowing up, okay, or it is controllable for small perturbations of the boundary data, that is initial data, okay, in particular initial data. So such behavior is called stability. That means your solution continuously depends on the prescribed data. So that is called stability. So these are the three fundamental things. Once you have a differential equation, one should be worried about existence of solution, whether solution is unique, and whether the solution depends continuously on the initial and boundary data. So may I request participant, somebody, I'm getting a lot of echo. Can you put off microphone on mute? Or maybe the organizer can force the microphone. So let me start with a simple differential equation. This is typically called initial value problem. dy by dx equal to f of xy, and y of x naught is y naught. So this is called an initial value problem. So for example, y dash equal to x, y dash equal to x plus y, where y of 0 equal to 1. So such examples can be thought of. So for such initial value problem, we cannot simply assume that solution exists. So the existence of solution depends on certain conditions on the right hand side f. So what is the Picard's existence and uniqueness theorem states? If the right hand side f, so that is this f, is a continuous function on some region, this is a rectangular region, so then the initial value problem has at least one solution in the interval where alpha is minimum of a comma b by k, where k is the upper bound of f. That means, first of all, you should be able to find an upper bound on f. Okay. So if that is k, then if your function is continuous on this rectangular strip, then the initial value problem has at least one solution in this interval. Okay, so this is very fundamental theorem in ordinary differential equations. Now the next question is, uniqueness,
In the mute వస్తది.
right? May I request somebody is talking. I would like to have no crosstalk. Kindly understand. So uniqueness theorem. So now the first Picard's existence theorem that we have discussed just now. Uniqueness theorem is, suppose not only f, the partial derivative of f with respect to y. So f and dou f by dou y are continuous in R. What is R? The rectangular strip which is defined just now. Then the IVP has at most one solution in this interval. Okay. So we are very much interested in existence. This is the existence theorem that is merely asking f continuous. In fact, that is a stronger condition. It's not merely, it's a stronger condition. Then you have uniqueness. So with respect to this theorem, a weaker condition is possible instead of continuity. This is called a Lipschitz continuity. So where L is a Lipschitz constant. So corresponding theorem holds with a weaker condition, but nonetheless, we try to put in general a stronger condition. So now let us look at examples. First one, du dt is u of 0 is 1. If you simply solve, you get the solution. What it indicates that, you see, your solution exists for all t greater than 0, right? For all t greater than or equal to 0. That means this is a global solution. Now in this problem, if you see, your solution exists within a finite interval. So this is a solution is not global. Okay, it is limited to an interval. Okay, solution is unique but global. Solution is unique but local. Now if you see this, you have two solutions. That means uniqueness is lost. So you do not have a unique solution in this case. That means you should go back to your Picard's theorem and verify whether this is satisfying Picard's existence and uniqueness theorem, hypothesis, etc. Okay. So the idea is, given a differential equation, one should be very much worried to understand whether the solution exists. If the solution exists, whether it is unique. Okay. And the next part, of course, is stability. Okay. So in today's talk, we won't be discussing about the stability, etc. Okay. But indirectly, we will try to show the solution existence and unique. Okay. So now let me take a simple example, Coulomb's law in electricity in the absence of any sources on the right hand side. So then what will happen is simply divergence of a vector, that is the electric field, equal to 0. If you write it in component form in 3 dimensions, it is this. And if you see divergence of 0 is a divergence of vector field is 0 and you solve for E, we just look at it. There is no way we can solve for this particular equation, because one equation, 3 independent variables. So the situation is very difficult, but so I put Poisson if there is a right hand side non-zero. So now suppose if you introduce a potential, E is grad V. Okay, so in BSc first course we have learned, if V bar equal to grad F, then F is a scalar potential. So similarly, suppose for this electric field has a potential, then divergence of E together with this will give you del square V is 0. So that is a Laplace equation. Okay, it's very straightforward. Divergence of E on this will be Laplace equation. Okay. So let us see the concept of classical solution. What do you mean by classical solution? Which all of us are typically using, taken for granted. Suppose there is no charge in the space, that means the right hand side is 0. That is the case actually. I have taken 0. This could be non-zero also. So then we have Laplace equation. Suppose in 2 dimensions, it is this. Now, when do you say some function is a solution of this. Any f satisfying del square f equal to 0 will be solution of this. Any f, if it satisfies del square f is 0, then it should be at least 2 times differentiable, isn't it? Because why? This is 2 times with respect to x, 2 times with respect to y. That means any function which is at least 2 times differentiable with respect to x and y, then satisfying this equation, we call it is a solution, right? So you are given something, suppose x square minus y square, f of xy equal to x square minus y square. So does it satisfy this Laplace equation? Yeah, so it will satisfy Laplace equation, right? So how does it satisfy? So it is 2 times differentiable. The partial derivatives 2 times exists and satisfies. Such solution is called classical solution. Then do you think some non-classical solution exists? Yes, that is a little bit modern. I will show you what is the technical term that will be used for such solution. Okay. So make a note of this. Maybe towards the end of the talk of part 1, I'll come back to this. Okay. So now suppose you have assumed that solution exists, okay, because right hand side is non-zero, and any f which is 2 times differentiable, it is a solution of this. So let us try to find such general solution. So that is our next step. And mind you, the equation is linear. Okay, so equation is linear. So since the equation is linear, we would like to exploit the linearity. Let us assume a separable form for the solution. Because the operator is linear, we are assuming function of x, function of y. Okay, then substitute in your PDE, which is the Laplace equation. If I substitute, what will happen? This is x double prime times y plus y double prime times x equal to 0. We are looking for a non-zero solution. Divide by xy, then you get this. Now you separate it. Suppose you take this to the right hand side, then what you get is x double prime x equal to minus y double prime y. One is purely function of x, another is purely function of y, and both are equal. This is possible only when both are constant. Therefore, x double prime x equal to minus y double prime y equal to some lambda square. From there, you get 2 ordinary differential equations. Okay. So these are the 2 independent ordinary differential equations, one for x, one for y. Okay. I think there should be a sign change here. Okay. So this is simple algebra. You can try. Okay. This is equal to lambda square. So first one we got it. And then this is y double by y with a negative sign is lambda square. So this should be plus, I guess. Okay. Now these are called eigenvalue problems in operator form. Why? If you take x double as an operator, so Lx equal to lambda square x. So that is of the form Lx equal to some kx, where k is lambda square. So it's a typical eigenvalue problem. 2 independent eigenvalue problems are there. So now the question is, how do we get the corresponding solution? Now let us look at a domain. So I have given a square, and let us see the boundary conditions on the square. So this is x equal to 0, okay, y-axis, then x equal to 1, line parallel to y-axis, then x-axis, then line parallel to x-axis. Okay. Now, if you see, these are the boundary conditions. I am prescribing all 0 boundary conditions. But what was our v? Our v was this. So 0y is x of 0, y of y, that is 0. Now, mind you, we are looking for non-zero solution, therefore y of y is non-zero. So we are getting x of 0. Similarly, we are getting, so we got independent boundary conditions for x and y. Therefore, what are the now corresponding differential equation for x? Simply this, subject to these independent boundary conditions. What is our boundary? 0 and 1. Okay, x is varying from 0 to 1 because it's a square. It is a square. X is varying from 0 to 1, and you got independent boundary conditions. Similarly, y is varying from 0 to 1. You got independent conditions. So let us focus on the eigenvalue problem for x. Okay, we said lambda square is constant, but we did not talk about the restrictions on lambda square. It could be 0, it could be positive, it could be negative, right? So let us talk about lambda 0. If this is 0, then x double prime equal to 0 will give us a simple linear function. Then if you substitute these, x of 0 is 0 will give you C2 is 0, x of 1 0 will give you C1 is 0, x is 0, trivial solution. Our aim is to get non-trivial solution. Now let us talk about lambda square positive. Then we get a simple structure in terms of exponential functions, and this is the general solution. These are the basis functions, e power lambda x and e power minus lambda x. Then C1, C2 are arbitrary constants. Therefore, this is the general solution. Now, up to here, no doubt this is general solution of this operator equation. But the moment you plug in these boundary conditions, first one, if you substitute, you will get C1 plus C2 0. And second one, if you substitute C1 e power lambda plus C2 e power minus lambda is 0, you will see that the system will be inconsistent. Okay, so you won't be able to. So again, so you get inconsistent. So therefore, no, I have to check this. So can you check C1 plus C2 is 0? That is C1 is minus C2. So then next one, if you substitute, so again trivial solution. Maybe I should not have written this. Okay. So now lambda square is less than 0. You can call it lambda square is minus k square or something, but I'm using the same lambda. In this case, you have the corresponding solution in terms of these basis functions, cos lambda x and sin lambda x. Now, if you substitute these boundary conditions, you get x of x equal to C2 lambda x. Then the next one will determine lambda, which is n pi, where n is integer. So it's very easy to check this. So what are the eigenvalues? The eigenvalues are n pi, where n is integer, and the eigenfunctions are sin n pi x. Okay. So that means we have solved first set of this equation corresponding to these boundary conditions, determine the eigenvalues. For those eigenvalues, you solve the remaining ordinary differential equation, then you get the solution. Okay. So that is up to now. We have determined the solution. And what will be the solution? Since you have integral values, for each n you get one solution. So what is the general solution? It should be linear combination of those, right? So you will get a series, summation of the series of these. Okay. So we have determined x of x and y of y. So therefore the solution will be summation over m. Okay. So you will see it very soon from now. Now the question to be asked, can we always obtain these eigenvalues? Because just now we have obtained, these are the eigenvalues for this Laplace operator. And we may be under the impression that we can obtain always. Okay, the answer is no. So let us see how the answer is no. Same operator, this time we are having a slightly varied data. What is the difference? Earlier we had homogeneous data. That means the function values are 0, okay, all the boundaries. This time we have one of the data is non-zero. That means there is a non-homogeneous data, okay. Now let us look at the homogeneous data. Again, similar argument, x of 0 is 0, x of 1 is 0, then again, now let us look at v of x1 is 10. So what happens here? Look, we have x of x into y of 1 is 10. And how do you determine which one is what? Okay. So there are infinite combinations, right? So in this approach, we are not in a position to get independent boundary conditions for x and y. So we are not in a position to determine the eigenvalues for non-homogeneous data. Okay. So the operator is linear, but unfortunately, we are not in a position. So how to deal with non-homogeneous boundary conditions? That means such data. Okay. So the next, how to deal with non-homogeneous boundary conditions. So consider the following example. Dou u by dou t is beta times. So those who are have done first course of PDE, these are the standard examples. The first one that we have seen is a Laplace equation, and this one is parabolic. Okay, this is a parabolic equation. This is a one-dimensional unsteady heat conduction. Okay, so now since it is two spatial derivatives, you need boundary conditions on x equal to 0, x equal to L. Okay, so this is a heat conduction in a rod of length L, and one time derivative, you need initial condition. Okay, so that means we have taken a rod, then one end we are maintaining some temperature, another end we are maintaining another temperature, then we have some initial temperature. With time, how the temperature is changing. So that's the model, right? So we are talking about non-homogeneous data. So going for separation of variable solution would not suffice. Just now we have seen. Therefore, what is the mechanism? We are seeking solution of the form. You see, u of xt is w of xt plus v of x, where v of x is time independent. Okay, so the operator is linear. So we are exploiting this linear structure, and we are resolving u unknown as explicit time dependent plus a steady part, so that you have this structure. Then you choose v such that since it is only spatial, it is no longer partial derivative, satisfying the non-homogeneous data, because this we can solve. So v of x, it's a linear function, then you apply these non-homogeneous data, then you get the solution. Then the reduced form of the time dependent, explicit time dependent part is this, subject to homogeneous condition. Okay, and of course the initial condition is changing because this v will come in place. Okay, so now we know how to solve this using separation of variables. Why? Because we have homogeneous data. Okay, so using similar approach we can solve. So let me put it the application little in terms of physics. A uniform rod of length L whose surface is thermally insulated. Okay, why it is insulated? Because both ends we are maintaining some temperature. Okay, and it is initially at temperature theta naught, at time t0, one end is suddenly close to theta 0 and subsequently maintained at this temperature. The other end remains thermally insulated.
Sir,
So that
cannot
means
hear anything.
Hello? Hello? You're not able to hear?
Please continue, sir.
You're able to hear?
Yes, sir.
Yeah, somebody said they cannot hear, so I was little.
Yes, sir. Yes, sir. Some network problems.
Okay. So this is a rod. We have insulated one end and one end 0, then an initial temperature, and with time, what is the temperature? That's what we want to understand. Okay. So this is our problem. Finite rod of finite length, boundary conditions. Insulation means flux. That means there is a flux accumulating. Okay, that is the insulating condition. So this is a temperature is 0, one end, and other end flux is 0, and boundary condition is initial condition is theta of x at time t0 is theta naught, which could be function of x. Okay. Now let us try for our separation of variables. This is the separation of variable structure. You substitute this in this PDE, then one is function of x, another is function of t, therefore it has to be constant. Now k is positive, this is the structure, k is negative, this is the structure, k is 0, this is the structure. With this structure, you substitute your boundary conditions. Previously, I explained when k is negative, you get a non-trivial solution. Other times, you get a trivial solution. So therefore, this is a negative. For that, I'm computing the solution. Very easily, you can compute. Why? Because when k is negative, this is the combination. For this combination, you apply the boundary conditions in terms of x. What are the boundary conditions? One is on x, another is on derivative of x. Why? Because derivative? Because of this condition. This will give us x of 0 is 0. This will give us x prime of L is 0. Okay. So with that, I'm sorry, this should be x prime at L, because this is L, x prime at L is 0. That will determine the eigenvalues. Okay. So these are the eigenvalues for these values of n. Therefore, the acceptable solution is of the form. Okay. Now, suppose your initial condition is theta naught x is some 2020 sine pi x by 2L. Okay. Which means you compare this with this. Okay. At t equal to 0, this term is vanishing. Now we are left with bn sine 2n plus 1 by 2L pi x. That must be equal to 2020 sine pi x by 2L. You can easily determine 5. I wanted to have 5 pi x by 2L. So n equal to 2 will give us, okay, n equal to 2 will give us 5 pi x by 2L. So I am giving B2 is 2020 and Bn is 0 for all n not equal to 0. So n, if you put n2, you get 5 by 2L, right? This is 5 by 2L. So in this series, Bn sine 2n plus 1 by 2L pi x, that means first term is B0 with sine pi x. Okay, right? So this, suppose n is 1, B1 sine 3 pi by 2L pi x. Okay, then B2 is B2 times 5 by 2L pi x. So like this, these are the modes. Corresponding to each n, you have one mode. So I made a mistake. I should have written 5 here, 5, because I'm giving B2 is 2020 and Bn is 0 for all other n not equal to 2. Okay. Essentially, whatever the functionality, we should compare with this and determine the n. Okay. So those who are interested in how these modes can be computed, this is a Gibbs phenomena. I don't know whether I can get time to show this maybe later. So Gibbs phenomena, if you click this, you can see different. So n is varying from 0 to infinity. Suppose somebody is considering only 5 terms. So then you will see a lot of oscillations. If you increase the number of terms within the interval of that, so then you will see a smoothing. So this is Gibbs phenomena. So you can pay attention later on. Okay. So that means we have a non-homogeneous data. Then we converted to homogeneous, and that homogeneous problem, heat conduction, we can solve using separation of variables. 3 cases, but non-trivial solution exists. Only one k is negative, and correspondingly we determine the eigen values and corresponding eigenfunctions, and corresponding to these eigenvalues, the T solution first order equation corresponding to that lambda, this will be solved, and that is given by this. Okay. And if you give some initial data, you can determine the coefficients. Okay. So this is about separation of variables. Now further application, suppose we are talking about flow past a sphere. Okay, it could be potential flow or viscous flow, etc. Then U is velocity potential and divergence of U0 together gives Laplace equation. This time I am showing you, since we are talking about sphere, flow past a sphere, you cannot use Cartesian coordinates to solve. The reason is, using Cartesian coordinates, you won't be able to fit the boundary condition on the sphere. So we are following spherical polar coordinates r theta phi, where phi is the azimuthal angle. Now again you go for separation of variables, function of r, function of theta, function of phi. So you may ask a question, why every time separation of variables, the operator is linear. Okay, the operator is linear, so we can exploit this linearity and try to separate the functional dependency with respect to each of the coordinates. Now you substitute this in Laplace equation, then you get coupled. Okay, there is some coupling with this parameter. So first you separate r part with theta and phi part, equate to a constant. That is, for convenience, we choose n into n plus 1. Then phi part you separate, call it m square. Okay, so we have 3 differential equations, one for phi, one for r, one for theta. Okay, then if you solve each one of them, we get this solution. R is having this polynomial structure. Theta is in terms of associated Legendre polynomials, and phi is having the trigonometric functions. Now the general solution structure is the series n0 to infinity Sn theta phi. I'm combining this Legendre, associated Legendre, with these azimuthal function and putting in this form. That is called Sn theta phi spherical harmonics. Okay. So now if you are giving your far field some, because it's a, hello? Yeah, so you can you can compute these arbitrary constants subject to some far field flow and boundary condition, the way the heat conduction problem, the B2 is determined. Similarly, if you are given some far field, let us say uniform flow is r cos theta, then only n equal to 1 will survive. Okay, so the remaining coefficients will be vanishing. So this can be done very straightforward manner. Okay, so this is about separation of variables for spherical geometry. Earlier one is separation of variables for Cartesian geometry, this problem, and this is a separation of variables for spherical geometry. So depending on the physics of the problem, we have to use the corresponding coordinate system. Okay. So now we have so far discussed separation of variables, but what are the other techniques to solve PDE? So there is a popular technique called integral transform methods. So how it works, you take a PDE and then apply your choice of integral transform depending on the PDE, which will reduce it to ODE. So that's the key advantage of even in separation of variables. That's what we have achieved. In separation of variables, we have converted PDE to ODE. Similarly, in integral transform also, PDE will be converted to ODE, then solve the ODE with respect to boundary conditions. Then solution in transformed space is obtained. Use inverse transform. Okay. So then the final solution. But mind you, even the boundary conditions also have to be transformed. Okay. So you get the final solution in original space. So let us look at the corresponding integral transform methods. Typical transform structure is given by this. Okay. You should have so a lot of typos, excuse me, because it's too tied up with a lot of works. Kindly excuse me. So this is this should be S and then DS. Okay. So this is the kernel of the transformation. Now, if you choose this kernel, it is Laplace transform. If you choose this kernel, Fourier transform, Fourier sine, cosine, Mellin transform. Okay. But for any arbitrary function, you cannot apply any transformation. Necessary and sufficient conditions for the existence. Okay. So these are there in the standard first course of ordinary differential equations. So they have to be. So my focus here is to show you application of that. So now again we have discussed a Laplace equation. We have discussed a one-dimensional heat conduction equation, which is parabolic. Now in terms of PDE classification, third category is left. That is the hyperbolic PDE. What is it? One-dimensional vibration of a string. So that means we are taking a string, okay, and then you are giving oscillations, displacement at one end, then you see a wave strike. So this is typically called wave equation. So a semi-infinite long string having one end at x equal to 0 is initially at rest. The end undergoes a periodic transverse displacement given by this. Find the displacement of any point on the string at time t. Okay. So this is a typical wave equation. So the corresponding wave equation is modeled in terms of this hyperbolic. Now, what is the difference between the heat conduction equation and this? Here, not only 2 times with the space, we also have 2 times with time. Okay. So the boundary conditions, one end is finite. Okay. So semi-infinite, that means as x goes to long distance, u is finite. Solution should be bounded. But whereas at x equal to 0, you are giving sinusoidal, like transverse oscillations. Initial conditions, u represents the displacement. So initial displacement is 0, initial velocity is 0. Okay. So how do we attempt? We are using Laplace transform. So if you apply Laplace transform with respect to time, you get a differential equation. So the basic idea of transform techniques, integral transform techniques, is to kill one variable. Okay. So here we have killed the time and transformed into the corresponding transformed space, which is a ODE, and we get the general solution. Now, since the displacement is bounded as x goes to infinity, this part is annihilated. So this is killed. Then we are left with this. Now, taking the Laplace transform of the boundary condition, then we get the solution. B is determined. We get the solution by inverse Laplace transform. Okay. So you can see this is typically a wave structure. Okay. So a very popular technique to solve wave equation. Okay. So now the question is, when you use such integral transform techniques, do you think always we can invert using the corresponding inverse transform. Okay. So it is not always possible to invert using the corresponding integral transform. For example, if the coefficients are very nasty, then it's very difficult to invert. Okay. So in this context, I would like to, I'm not sure how many of you have heard this. This is very handy tool if you have complicated coefficients in your equation and your numerical, your usual Laplace transform inversion is not working. So then how do you solve using numerical inversion? It is very popular, Durbin's inversion. So Durbin's algorithm, this structure is given. That means if f tilde is the transformed function, so then how to retrieve f of t? So this is the inverse transform. It is Durbin's inversion. So where f tilde of sk in terms of transform variable has a specific structure, and er is the tolerance, up to what tolerance level you get. Okay, so general default value is taken. So with this, we are showing you numerical inversion of this e power minus sin t. Okay, so numerical inversion and analytical plot, they agree very well. Okay, so I am sure many of the colleagues will be struck with the inversion, so they can try this Durbin's algorithm. Okay, so now playing with a small parameter. So we have discussed the separation of variables, then integral equation approach. Okay, so now let us go to a slightly new. Okay, so we are going to a slightly new concept. Okay, so this is also very much used in the research community. So playing with small parameter. Okay, so of course, if you see this equation as such, there is no parameter. Okay, it's a simple first order differential equation with this initial data, and if you get a solution, you have this. Okay, now I am considering a slightly perturbed equation. Okay, so the perturbed equation is, here you have a small parameter multiplying another function. Okay, so this also you can try, but this is nonlinear. Okay, this is nonlinear. Epsilon is a small parameter. Now let us look for a solution of this form. That means y we are approximating as y0 of t epsilon y1 of t plus epsilon square y2 of t, so on and so forth. Substitute this in here, then collect the coefficients of each order. That means this is coefficient independent of epsilon, this is coefficient of epsilon, this is coefficient of epsilon square. Yeah, you get hierarchy of problems. This continues. I have shown it only up to epsilon square, but this continues. Okay, so now corresponding initial data, it is independent of epsilon, therefore that is going with this, the remaining is 0. Now how did you get this? Again, I'm repeating, you substitute this in here, expand, collect the coefficients. So order 1 means this is big O notation. That means so the functions which are constant multiples. Okay, functions which are epsilon multiples, functions which are epsilon square multiples. Okay, so you can solve each one. If you solve these hierarchy of problems, you get these. Okay, now what was our assumption? Our assumption was y0t epsilon y1 plus epsilon square y2. We got at least up to second order. Therefore, what is the solution? This is y0 epsilon times y1 epsilon square y2, and due to lack of resources, that means I am lazy to compute, let us say, I am dumping the higher order terms as order of epsilon cube. Why? Our assumption is for the given ODE, the solution exists and it is bounded. Okay. So therefore, the solution is bounded, and what is the next order term? It is epsilon cube. So therefore, from here, I am careless, or I am lazy, or I have lack of resources. Therefore, I am almost ready to throw it. That is the notion. Now, if you see this, as epsilon goes to 0, this goes to 0, this goes to 0, and this part is anyway much more higher than these two. They go 0. You are getting y0. So let me explain. You have first this equation whose solution is this. Then we have added a small disturbance or perturbation, assumed this form. Then we got the solution up to second order. Now in the solution, if you go to epsilon 0, you are getting leading order solution, and operator also, if you goes epsilon goes to 0, this is the operator whose solution is this. Okay. That means we say this is a regular perturbation of this operator. Okay. What do you mean by regular perturbation? I am adding a small perturbation such that not only the operator is agreeing with the original unperturbed operator in the limit of epsilon goes to 0, the solution also agreeing with the solution of the unperturbed. Okay. See, here I am putting equality, but it should not be. It should be approximate. Why? Because there is a large dump error. This is the error. Okay. If I'm ready to throw it. Okay. Because epsilon is small parameter. So somebody will say, okay, you can throw from epsilon square. Somebody will say, no, you can only throw epsilon cube. Why? It depends on what is the value of epsilon. Okay. So this is a concept of regular perturbation problem. Okay. This is regular perturbation problem. Now, what is then irregular? Look at the boundary value problem. Here also you have an epsilon. Okay. It's a second order equation, therefore you need two data. Now let us say you are expanding like this and collecting hierarchy of problems. Okay. Now as epsilon goes to 0, this part is going to 0 and the order of the equation is reduced by 1. Okay. As epsilon goes to 0, because the small parameter is multiplying the highest order derivative, the order of the equation is reduced by 1. Okay. So this is a little disturbing. Okay. So why it is disturbing? Once the order of the equation is reduced by 1, you can never get a solution that satisfies both the data. Okay. Of the original problem. Original problem, yes, you can get satisfying this data. So if you take epsilon goes to 0 there, you cannot expect a solution of this to satisfy these two data. Okay. So there is a difficulty. Okay. So as epsilon goes to 0, this equation is this. So therefore, simultaneously, both the conditions cannot be satisfied. So this is called a regular perturbation. It's a singular perturbation problem. Okay. So the earlier one is a regular perturbation problem where operator epsilon goes to 0 is agreeing with this operator, solution is agreeing with the solution of this operator. Everything is very controlled regular perturbation. Whereas here there is a uncontrolled mechanism here, because one of the boundary there is a difficulty. So there is, that means the behavior, it's not a smooth transition. one cannot get a uniformly valid solution in the entire domain using this approach. So you have to develop a new mechanism that is called method of matched asymptotic expansions. Okay. So it will take some time. So I'm slightly, it's involved also technically. So all that I'm trying to say is you have to develop one solution which is called outer solution, then inner solution, and then match it. Okay. So now I promised you in the Laplace equation, if f is 2 times differentiable, okay, and continuously differentiable 2 times at least, and if it satisfies Laplace equation, then we call it classical solution. Okay. Now let us consider this steady heat conduction problem 1D with a non-zero f and u is 0 at x equal to a and x equal to b. Okay. I am going to introduce something non-classical. I told you, but the corresponding technical term already the heading is giving some hint. So on weak solution. Okay. So what is that weak solution? So in general, if f is continuous, okay, then we have a smooth solution. Okay. Now what we are doing is you take a smooth function phi that vanishes on the boundary. That means phi is differentiable, and not only that, since u is vanishing on the boundary, we are choosing a phi which is also vanishing on this boundary. Then multiply this equation and integrate from a to b, then do integration by parts. So again I'm repeating, multiply this equation both sides with phi, integrate a to b, integration by parts. The first one is this, second one is this, and right hand side of course it stays as it is. But what is our phi? Phi is vanishing at b and vanishing at a, therefore this part is vanishing. Okay. That means in some sense this equation is equivalent to this equation. Solution of this will be solution of this. Okay. But what is the restriction, condition, requirement on you? If you want to solve this, then it is simple that u is required only one time differentiable. Okay. Whereas the original equation is 2 times differentiable. Okay. So that means original equation is demanding 2 times differentiability. So any f which is 2 times differentiable satisfying the equation, that is a classical solution. Whereas any u which is 1 time differentiable satisfying this integral equation is a weak solution. And what is weak? The regularity, the differentiability requirement is reduced from 2 to 1. That is the weak solution. Okay. So if you generalize for a Laplace equation, you can generalize, okay, for in general. So what is this weak solution? I'm giving a simple example. So you have Burger's equation, nonlinear. You cannot use the separation of variables, and with the split data. Okay. So then for this you have this discontinuous solution. Okay. So for x less than 0, 0, for x greater than t 1, and what is there? Okay. So u2, the gap, you have this. So this is the weak solution because there is a discontinuity. Okay. So it's not differentiable as many times as the order of the as the derivatives requirement on the equation. Okay. So more or less I'm done with the first part. So where I have started with separation of variables, then homogeneous boundary data, then non-homogeneous boundary data, then integral transform, and I have also shown Durbin's algorithm where one can solve using numerical inversion. So then we move on to with respect to ordinary differential equations, perturbation, I briefly explained singular perturbation, but in detail that requires a lot of time. Okay, so regular perturbation is easy to understand, but singular perturbation, method of matched asymptotic expansions, it requires a lot of time and effort. Okay, and then towards end, I have introduced in brief what is a weak solution. That means the regularity requirement, the differentiability requirement on the function is reduced. So that is of course under the integral sign subject to some support function phi, that is called test function. So this concept is called weak solution. Okay, so now we move on to the application part. Okay, so that is the second talk, my second talk. Yeah. So is it visible? Hello?
Sir.
It is visible, sir.
So is it visible, sir?
Yes,
Yeah, it is
sir.
visible, sir. Visible.
Okay. So I promised that some application I will show. So this is our research work, which we have been doing with my PhD student. He just graduated. So I'm going to discuss lubrication process inside a human knee joint. Okay. All of us, we realize at some part of our life when we are getting old, and these days it is very common that we have knee problems. Okay, just 45 plus people are developing. So I will show you in brief the mathematical model and then what we have achieved. Okay. So in order to understand, one has to know the definition of porous media. So porous media is our tissue, sponge, sand. Okay, so you have a solid and have space in between fluid to pass through. Okay, so any material like this is called porous media. And what are the two quantities that are important for porous media? One is the porosity, another is permeability. So porosity is the measure of how much of a rock is in open space. Okay, suppose you take a small vessel and you put maybe some 100 grams of mustard. Okay, and the vessel is big. You put 100 grams of mustard and then you just spread it. On the other hand, put 200 grams of mustard and then you spread it. So then naturally the porosity, because the volume is more no, in 200 grams, that means the porosity is less. Okay, so that's what. Permeability is the measure of ease fluid can pass through pores. Wood, it's permeable. Filter paper, permeability is more. Okay, so that's what the permeability. Okay, so permeability certainly depends on the connectedness. You see here highly porous but poor permeability because it is not connected. Here see high porosity, good permeability because there is a connectivity and everything. Okay, so it is like this. Now in soil you have a lot of gradation. See, fibers are aligned like this and here fibers are aligned like this. So what I'm trying to say, permeability has to be direction dependent, permeability spatially dependent. See, in glass the fibers are aligned very randomly. Okay, that is how many times permeability is used as a scalar. Okay, but in general many of the applications it is not scalar, it is a tensor, direction dependent. How you see the fibers in 2 dimension, suppose the fibers are aligned at an angle, then you can define something called anisotropic permeability depending on the angle. So you see sugarcane, we always peel it like this because the fibers are aligned vertically. That means the permeability is more in the vertical direction. Suppose sugarcane, if you try to cut it like this, it will be hard. Similarly, you see some trees, if you cut it, there are round circles. It is easy to peel it like this because permeability is more in the vertical direction. Okay. So the fiber alignment will dictate the permeability. So in 2 dimensions, the anisotropy structure can be given like this. So those who are good at understanding physics, permeability, they can correlate with thermal conductivity, which is depending on the direction, or magnetism, magnetic permittivity, that also is same. Okay, so you can get some idea. So here our take is we are more concentrated on anisotropy. Okay, so that is there are 2 principal direction parameters, and there is one parameter which is controlling the alignment of the fibers. Okay, it's easy to understand. Suppose you keep some papers, squeeze it like this, okay, with foldings, then you try to sit, so it can take a lot of weight. Okay, because the permeability structure, fibers are aligned vertically, so it can. Okay, so these are some ideas. Now, what is a squeezing? Squeezing is prescribing a load. The target of today's talk is lubrication process in knee joint. That means there is a squeezing involved. Why squeezing? All the time you're walking, so there is some load, periodic movement is happening. Okay, load is applied, load is released, load is applied, load is released. So when you are putting load, there is a squeezing happening. What kind of squeezing? I will show it to you. So this is the cartoon of knee joint. You have upper plate, lower plate. This portion is cartilage. Cartilage is a little hard, little soft, porous material. It's a tissue, fiber. And in between, you have complete fluid, which is viscous fluid called synovial fluid. Okay. And these are called femoral condyles and tibia plateau. These 2 are porous materials, and this is the bone. Top is bone, this is bone. Okay. And these are some buffer areas. When you apply load, this plate is coming down, then synovial fluid is going inside, but this plate is not touching. Okay. When do you feel the pain? When the upper plate will touch the lower plate, then you will feel the pain. Okay. So when this cushioning, squeezing flow cushioning is happening, the fluid is acting as a resistance, viscous fluid, then it is coming into the cartilage. If the cartilage is very smooth, then it will come and collapse and hit the lower plate. Okay, which is not good. How, if you see micro scale cartilage structure, the cartilage structure is the deep bottom fibers are aligned vertically, middle random, and upper superficial, they are top. So when the load is coming, they are little taking the load, then arbitrary orientation is stopping, and finally when a lot of load is coming, the deep fibers which are vertical, they are holding the load. Okay, so it's so beautiful, the structure of the cartilage, it's very interesting. Okay, now we want to model it mathematically. Okay, so since the cartilage fibers are anisotropic, we are considering as an anisotropic porous bed, and this is the bone. So nothing, it's like a solid synovial fluid and upper bone that is coming with the applied load. So we are putting our leg, so on the floor we are walking, then there is a periodic loading, and then you're releasing. So this is a squeezing happening. Okay, so there is a lot of squeezing happening, then the fluid is going to the gaps and into the porous media, okay, the cartilage, and then when you release again it is coming, so nicely acting. Okay, so we want to study. So what are the any fluid mechanical problem, you should have corresponding conservation laws in place. So in the gap, it is a completely fluid, synovial fluid. So this is a conservation of mass, assuming the fluid is incompressible. And this is a balance of linear momentum. This is a local rate of acceleration. This is convective rate, the pressure forces, viscous forces, and body forces. This is called Navier-Stokes equation. Kindly excuse me, those who are not expertised with this. Okay. Then in the anisotropic cartilage, we are modeling something called Darcy equation. It is similar to fixed law of diffusion, okay, where K is the permeability, which is a tensor in our case, mu is viscosity, okay. So you have two set of governing equations, here Navier-Stokes, here Darcy, and we couple them. This I have already shown, so I'm skipping. Then if you look at the Darcy equation, divergence of V, if you apply on this with K being a matrix, you get a single equation for pressure. If K is constant, P is Laplacian. Here K is not constant, therefore you get a anisotropic Laplace equation for P. Okay. Okay, when K1 is K2, so then you get a simple isotropic Laplace equation. Okay. Then what is the net force exerted on the bearing? Bearing means the top plate. So that force is calculated. Then you have to write a, this is a first course of physics. This is the equation of motion of the bearing. Okay. So in even now +2 we have this. Okay. So this is the equation of motion of the plate. Okay. You simple force balance. This is the applied load, and this F is a force, and this is the corresponding mass into acceleration. Why? What is H? H is the thickness of this fluid layer. When you are applying load, this plate is coming down, H is changing with time. Okay. And when you are releasing again, so H is changing with time. So that is why there will be a dynamic equation for H, corresponding dynamic equation. Okay. And then we have to fit some boundary conditions. Okay. So we fit some boundary conditions. For example, upper plate, the velocity is 0. This is the horizontal velocity. Vertical velocity should take the velocity of the plate. dH, H is the width, so dH by dt is velocity of the plate. Okay. So we fit the various, and also at the interface, there is a Navier-Stokes equation and Darcy equation. At the interface, there should be momentum exchange. There should be corresponding interface conditions. Okay. So this is a little bit technical. So I'm sure those who are not expertised in fluid mechanics, it's a little difficult to understand. So at the interface, I want to give you an application. I will show you the results instead of more of this technical part. So you assume that whatever flow coming from a fluid, it is going into the porous media. So that is, you can intuitively understand. Okay. Why intuitively you can understand? You are pressing, then the flow comes, and this is porous. If it is non-porous, everything will escape. If it is porous, something will go into the anisotropy, right? So that's what. So with these interface conditions, we solve the problem. Before we solve, we do a non-dimensionalization, and we are going for a small parameter. What is a small parameter? HP by L. What is HP? Is the width of the porous layer, okay, and length of the knee. So it is very small. So epsilon is small parameter, similar to our singular perturbation problem. So we introduce such an epsilon, and we try to, you see, epsilon is multiplying higher derivative. So it is not a regular perturbation, it is a singular perturbation problem, and we solve it. So I'm more interested in showing the results. So these are hierarchy of problems similar to ODE that I've shown. So this is not so much important for you. So then we estimate, okay. Look at it. Lambda is the anisotropic ratio. Lambda is K2 by K1 and H is changing. In the non-dimensional form, initially H is 1, then how it is changing with the lambda, okay. If lambda is 0.5, lambda is large. So when the plate is initially you are applying some load, up to some time there is no movement of the plate. Why? There is a lot of resistance of the fibers, okay. Until a threshold value, you will have to overcome that resistance. The moment you overcome the resistance, the upper plate starts to moving. Then again, the anisotropy, the arrangement of the fibers will show significant impact towards the bottom plate, and there are deviations in the time. So when lambda is large, you have an early, that means if your vertical permeability is more, so it is coming and then just touching the plate, okay. So the bottom plate. On the other hand, if the vertical permeability is small, 0.5, so then the contact is delayed. So this is when the upper plate is establishing the contact, okay. So we are interested in analyzing the contact time, right? So this is very useful, and we have another parameter which is the anisotropic angle, again with the alignment of the fibers, okay. If the fibers are completely vertically aligned, you get a lot of support, okay. See, suppose fibers are aligned like this, you get a lot of support. Suppose fibers are aligned like this, they'll collapse, okay. So that's what is happening. If phi is 90, then the contact time is delayed. If phi is horizontal, then the upper plate will touch the lower plate. You may see why there's such a micro level variations and all that. Why? Yes, the length scales are very small of the human knee, and the permeability lubrication mechanism, the permeabilities are very small, and the process is very small, very small length scales. So therefore, you can see we are plotting on the logarithmic scale, okay. So we are interested in analyzing the contact depending on the fiber alignment, okay. What is the benefit of it? The benefit is it can give an advisory. Suppose beyond some stage somebody is feeling knee pain. What does it mean? It means that the lower plate cartilage fibers are soft. They are soft. Then these days there is a medicine called Colaflax, or some people there is Ayurvedic medicines, they eat some seeds, etc. So then that will grow the tissue in the cartilage, so that the fiber alignment in the cartilage is grown stiff in the vertical direction, so they withstand the load, okay. So depending on the permeability of the cartilage, we can give the contact mechanism, okay. So that is one. And when the upper plate is pushing, okay, upper plate is pushed, then the streamlines are going. So the streamlines, the X and Y position of the path has a dynamical system we have captured in terms of various parameters. It does not make any sense to you because all the parameters has their own meaning, but I want to show the dynamic nature structure, okay. Okay, this is a dynamical system, and we through that we are solving. You see, with the symmetry I am showing, upper plate is pushing, then what happens? Some fluid is coming and escaping, some fluid is going to the cartilage, okay. See, now this will help us. Suppose you estimate the volume flux going into the cartilage. The moment you realize the volume flux is not going into the cartilage, you can flag, you can say that cartilage is hard, there is a possibility of knee pain, okay. So it is very much essential to understand the critical paths. Okay, so this is the critical path. That means above flow is escaping, it is not coming. Below flow is going inside. That is a critical path. So if the critical path, if you are establishing, you see here more volume flow is going into the cartilage compared to this. That means this will keep the cartilage very healthy. Why? Because there is no mechanism to supply nutrients to the cartilage. So you need more volume flow into the cartilage. Okay. So through synovial fluid, some nutrient goes in and the cartilage becomes healthy. Okay. So it is very much essential to capture. So this mechanism, we are estimating the contact time and how the cartilage can be kept healthy. So that is the idea. Okay. So we have identified some literature based on which the length, porous layer thickness, anisotropy ratio, viscosity of the synovial fluid are captured. This is real data. For that, we have estimated the contact time. Okay. So this is the contact time for this anisotropy ratio. Okay. You can see if the anisotropy ratio is smaller, then the contact time is delayed. Okay. So what is our conclusion? We have estimated the non-dimensional contact time. Then this is the real data, and a human normal person makes order of 10⁴ steps per day. So therefore, using that, we have calculated that approximately for the given load, okay, for the given non-dimensional load, one can withstand the load without establishing contact of the lower plate in the range 30 to 47 hours, which is much larger than 24 hours. Okay. So that means for a given non-dimensional load, okay, this is the load, what we are estimating, how these fiber alignment, that is lambda, for a particular lambda, this plate is able to withstand the load and it is not coming nearby. The moment it comes nearby, there may be pain, and in extreme cases, the cartilage will be damaged. Okay. So this study is based on singular perturbation that I have explained to you, and based on real data, we have estimated this. So this is an application of what we have been doing. I'm extremely sorry because this is just to give you an idea, not the technical derivations, etc. So I want to show you the model followed by the results to give some idea of how differential equations can be applied. So those who are interested, they can see this our group publication. Okay, so this is my PhD student, and we are also working on mathematical analysis and biological tumors, which is completely application of partial differential equations on identifying parameters for necrosis, etc. Okay, so these are some references. So those who are interested on understanding squeezing phenomena, okay, very classical work, squeeze film behavior of porous annular disc, and also Prakash J and Vijas K. So these are very classical work, and we have also contributed in this direction anisotropy. Okay, and we have some experimental work by my, okay. So these are some of our thoughts I would like to share. So thank you for your kind attention, and if you have any questions, I'll be happy to address. I hope I have not exceeded my time given.
Yes, sir.
Yeah.
Thank you, sir, for being with us and deliver excellent talk on and nice presentations on analytical and semi-analytical methods to solve PDS and its applications. Thank you very much, sir. Participants, please ask any questions and doubts regarding this topic. Participants, please ask any questions and doubts.
Okay, I'm seeing on the chat, some people are asking to share, etc., some papers. Maybe, madam,
sir.
I will share some of my papers with you all, so you can share it to interested people.
Okay, sir.
Okay. So people are asking, so I'll be happy to share. So
Okay,
I will share it to you organizers and kindly requesting them to share it to the participants.
Okay, sir.
So seems no questions. Mathematical modeling book. Okay, some are asking mathematical modeling book. I will suggest. That's good. Okay. Yeah, I'm seeing on the chat board, madam. So people are typing. So you have 1 minute, 2 minutes to see that.
Okay, sir.
Yeah, I'm just seeing. Yeah. Okay, so that is fine. So I will share the mathematical modeling book and my publication details. Kindly share it to the participants. Once again, thank you very much for giving me this opportunity.
Thank you, sir. Before invited talk of Dr. N. Vamsi Krishna Garu, introducing chief guest by B. Srinivasrao Garu, SG lecturer of our department.
Okay. Are you visible? Are you visible? Shyamlata? Shyamlata?
Sir.
Are you visible? Okay.
Sir.
Visible or not? Is it visible?
Sir, introducing of chief guest by B. Srinivasrao Garu, SG lecturer of department.
I'm ready. Is it visible?
Yes, sir.
Okay. Good morning, one. Morning, one and all. I'm B. Srinivasarao, Associate Professor in Mathematics, and I wish you to introduce Dr. Vamsi Krishna Narla. So Dr. Narla Vamsi Krishna is an assistant professor in mathematics. Currently, he is working as assistant professor of mathematics in Geetham DU2B University, Hyderabad. He has 15 years of academic experience in teaching. Coming to academic qualifications, in the year 2000, he completed his graduation from ABR Government Degree College, Repalla, Guntur district. In the year 2004, he completed his MSc Mathematics from JNTU, Hyderabad. In the year 2010, he completed his MTech in Computer Science and Engineering from JNTU, Hyderabad. In the year 2015, he has awarded PhD in Biofluid Dynamics from NIT Warangal. His main research work is in peristaltical transport in curved channels. Coming to publications, till now he got published 19 research articles. Also 7 articles are needed to publish but got acceptance from Scopus. He has attended 4 conferences and presented 11 papers in conferences. Also, he has attended 13 workshops. He worked as a coordinator from 3 workshops from Geetham University. Coming to award section, he got 2 awards, one from Andhra Pradesh Science Congress in the year 2018 and another from Summer Research Fellowship sponsored by IASC Bangalore, INSA New Delhi and NASA Allahabad in the year 2012. He has also published a book on title of Applications of Lie Algebraic Method in Vibrational Spectra of Molecules in the year 2017. Thank you very much. Thank you. Thank you.
Thank you very much, sir, for your nice introduction.
Okay, sir. Thank you.
Thank you, sir. Now I invite Dr. N. Vamsi Krishna, sir, to deliver his talk.
Yeah. Thank you very much to the organizers of Sri C.R. Reddy College, Eluru. And actually now I'm in the situation as after with a lot of
Sir,
yeah.
please
Is it
share your
visible?
video, sir.
Yeah, sure. Am I visible now? Is it okay?
Yes, sir.
Yeah, right.
Okay, sir.
Yeah. I am very much thankful to Professor G. Rajshekar sir for his wonderful lecture and also giving me the chance to share my knowledge in this workshop. And also I congratulate Professor Jan Mohan Rao and Srinivas Rao Garu and his team to organize such a nice webinar. I am going to start my talk. I am sharing now. Is it visible to all the people? Actually, I need this. Yeah, is it visible now?
Yes, sir.
Mathematica.
Essential fundamentals of
Yes,
mathematics
right.
and differential equation.
Yes. Yeah, actually, I need a complete screen. That's why, I mean, if it is required, I will on my video because it is covering this video is covering the screen. I require the entire screen. So, sometime I will mute my video. Okay. Yes. See, those are new to this Mathematica software. It is they will excite very well, and those who are working in this Mathematica, they will feel a bit bored because it is very fundamental. The concepts which I am going to deliver, essential fundamentals of Mathematica to differential equations. Here, when I click the icon of Wolfram Research Mathematica, we will see this kind of screen.
Sir.
Yeah, pardon?
Loudly, sir. Please loudly say.
Yeah. So you can see the screen of the Mathematica here. Here, left top corner, you can see file, edit, insert, format, cell, graphics, evaluation, palettes, window, help. These are the things are there. When we open the file new, we will have to open a notebook. This is a new notebook I opened. Here it seems a new notebook. Here in Mathematica, we have two parts. One is front end, second one is the kernel. Front end means the user interface, which we are going to see in the screen. This is the front end. This notebook untitled one, this notebook is the front end. Back end, we call it is the kernel. Generally, user sends commands to kernel through this front end. This is called a notebook. What we do using this notebook, what we do means here in the notebook, we can type the text, we can give the commands as an input, and also that the inputs received by the kernel and sends back the PostScript code and it displays in this notebook. That means front end. So we can use this notebook as a notebook text. We have to write the text, to type the text, to show the text. Because here, if you see in the screen, this is a notebook. Here, I made it as a slide for my presentation purpose. You can use this notebook as a slides. And this notebook, right side corner on the screen, if you see, there are some boxes, rectangular boxes. These are called cells. Suppose which I highlighted this cell, it is a title cell because you can see here title. We can make it as a subtitle, section, subsection, text, and also we can make this cell as a code cell, input cell, output cell, many things. So what are all these things? See, when I'm giving the presentation to the students or anywhere, we require all the things. We need to do some calculations. We need to perform some programming codes, and we need to present some graphs, plots, graphics, and sometimes we have to type like this kind of material. So this is the advantage of Mathematica. We can make all the things in one platform. So here I use like a presentation. I'm going to show slideshow. When I'm starting the presentation, it comes like a PPT. Essential fundamentals of Mathematical to differential equations, so and so. When I move to next slide, it gives the outline of my presentation. First, I will introduce what is the Mathematica, the basics of the language. But in order to go to differentiations and to solve the differential equations, what are the things we require? And I also explain limits, continuity, derivatives, and integration, how to perform in Mathematica. Here, why I'm doing this one mean, in most of the softwares, if you see, if you give an input, even in your calculator also, it produces the output. But Mathematica has the ability to give even what are the steps are there. The step-by-step nature, things also it will give. Step-by-step, how it is solving the problem. Each middle steps also it gives you. We will so see that one. And also, we can represent a beautiful presentations by plotting the graphs. Not only plots, we can animate it also. Animations also we can make, that we are going to see in that one. And also, I will touch some applications to differential equations, means solving some differential equations. Already, Professor G.P. Rashekar sir taught some techniques to solve the differential equations. A few techniques I will explain on how to code these things in Mathematica. These are the things we are going to learn in this section. Now I am coming back to our original state. That means I am coming back to the actual state. So now this is actual platform to perform the code. See this one. Mathematica kernel, and second one is engine. Front end is the user interface. User sends the command to kernel through front end. Kernel sends back the PostScript code that displayed in the front end. This notebook is an interactive document. It combines text, graphics, calculations. Not only these, many things are there in Mathematica we can do. Even we can do the technical computations like neural networks, data science, image processing, machine learning, even some visualizations also we can do. All the mathematics, whether it is pure mathematics or applied mathematics, what are the things are there, all the things we can do in Mathematica, all the computations we can perform. That is the ability of this Mathematica software. It is a powerful symbolic coding software. Symbolic computations, even we can do in other platforms like MATLAB and all that. Now it won't supports much, but Mathematica supports very well these symbolic computations, and also very extensive programming we can do. Very good programming. Numerical programming we can do using this mathematics. Now we are going one by one. See, in Mathematica, we can do general computations like this is now if you see, this is the cell. Here it is the input. I mean, this is a text cell. I am making this as a text cell. This is the text cell. Suppose if you go to the next cell, this is the cell. What it is showing, it is the input cell it is showing. That means it takes as an input. What is the input? 2 plus 3. 2 into 5 plus 3. 2. If there is a space between two letters, Mathematica consider it is a multiplication. No need to type star or these things. Space is the multiplication. Pi, capital P. I is the pi. You can see here. It is showing only the 2 pi value. If you want to see the numerical value of this value, you just give this command n in the closed bracket 2 pi. In Mathematica, any command, the command start with capital letters, and the argument of the command we have to give in the closed brackets. This is the syntax in Mathematica we follow. In different languages and different tools follow different syntaxes based on their architecture. This Mathematica, in Mathematica, the first letter is always capital N. The command start with the capital letter, and argument we will give in the closed bracket. We have to remember this one. If you see this one, the assignment, values assignment, A equal to 5, B equal to 3, C equal to 7. Equal to means it won't equate the value to C. It is not a variable which we are equating. It is an assigning operator. It assigns 5 is assigned to A, 3 is assigned to B, 7 is assigned in C. It considered as a global variable. See, here in the data types in Mathematica, no need to declare what it is. It is automatically understand the value based on that. Suppose if you give 5.2, it considered as a real number. Okay. In curly braces, if you give some comments like this, it considered as a vector. That means the first component vector is this one, second component of the vector is this one, third component and fourth component. If you this is complete component I am giving. Okay, I am doing this first one. See, if you execute this command, execution means in the cell we have to at a time press shift enter, then this cell will be executed. See, it is the root 5. If you want to get the numeric value n in the closed brackets square root 5, the command of the square root is sqrt. In the closed bracket, the argument value. Suppose if you want to see more number of digits, I am giving just like n, capital N, numeric value of square root of 5 up to 10 digits. It gives up to 10 digits. See, this Mathematica is a very friendly language because all the commands are user friendly. A general way how we are using words, in that general way of commands are there. For example, if you want to integrate, the command is integrate, I capital. If you want to plot, the command is plot. If you want to solve some system of equations or a quadratic equation, the command is solve, solve, that's enough. There is a big expression is there. If you want to simplify that expression, the command is simplify. So regular context, what are the things we are using? Those are the commands here. But you need to understand the syntax. See the simple commands here, sin pi by 4. One minute. Sine of some value, sine of pi by 6, cos of pi by 6, if you do that gives the values. If you want the numeric value of these things, put a capital N of something. And see these simple commands. If you run these commands by at a time pressing shift enter, these commands will be executed.
Dr. Vamsi.
We can also.
Dr. Vamsi.
Sir.
Sorry to disturb you. Can you be close to the microphone?
Yeah, sure, sir.
Yeah, your audio is coming and going, and participants are saying, I'm seeing the chat box. So kindly be close to the microphone.
Okay.
Sorry for disturbing.
Yeah, sure.
Thank you.
Thank you, sir. Thank you very much. Is it now okay, sir?
Yeah, thank you.
Okay, thank you, sir. Yeah, if you can see, in terms of radians, we can give, in terms of degree also, we can give all the things we can do. These are the simple commands we can produce. If you put the capital N in front of this one, it gives you the numeric value. Logarithmic values, the command is log. Logarithmic, natural logarithm it produces. If you want common logarithm, comma 10, it gives you common logarithm value. If 10 is not there, it produces natural logarithm value. So the base we can give here, comma, the base value. Whatever the base value of that log, you can give in that command. So these are the basic commands which we use in Mathematica, in programming. So this is also a random value it takes. See here, clear A comma B. I assigned previously A equal to 2, B equal to 3, something, some values. When I'm using, it takes as a global variable. When I use A, it assigns always whatever the value previously I used in that A, I assigned to A, that it takes. I don't want, because I'm using a new A here. That's why I'm clearing that value. There are two commands are there. One is clear, another one is remove. Remove means completely removes the A from the database. Clear means only it clears the value. Now, I'm assigning some random value. So it produces A. I'm assigning some random value. That random value is something it takes. A. B is assigned to another random value. It automatically takes it picks up some random value from 0 to 1 input. And another one is a very important thing, user defined functions. Here, suppose if I am defining the function like this, f of x equal to x cube minus 3x square plus 5x minus 7. If I execute this command, what happens? It is not substituting the a value in place of x, because if you give in this way, the syntax won't consider it as a function of x, which is assigned this expression. The functions are defined in this fashion. That means we have to represent f of x underline that equal to whatever the function you give, it considers as a function f of x. Now, if you replace x by a, put in place of x a, it is substituted in this value. So functions are defined in this way. What is that? F of closed bracket x underscore equal to semicolon. In old versions, the syntax in the syntax we have to give the semicolon. In the new versions, even though if you don't give the semicolon, it works, no problem. And also we can check what is this function. Question mark in front of anything, any command, any variable, if you give, it gives the details of that command or variable. So let me see what it gives. It is a global variable or global function. It produces like this. And I'm defining some function, expand, this is the command, expand, expand x cube. F of 2 expand x cube plus 1. I'm giving input as a plus 1 in the first function and a plus 1 in second function. You see the difference. And argument types also we can specify. Suppose, for example, if my function input is only integers, we can specify the argument type n underscore integer and function. See this one. If I give integer and real number, if I give 5 as an integer, it evaluates the value and sending the output. But if I give the real value, it is not allowing to send the output. But because it is not an integer, because I restricted to my variable is integer. See, in every defined command, first letter must be capital. And in the next example, I used a real number as an input. But what happened to this 2? See, real number means for the Mathematica software, 2 dot means it is a real number. Dot is there, then only it considers as a real number. Otherwise, it considers as a integer. Suppose if you put dot, it gives the value. Otherwise, it produces the same thing. If you don't give the dot, it considers the integer, but any other numeric value. Only when we put dot, then only it recognizes. Clear? Next, positive integers also we can give like this. If you give the negative numbers, it won't allow you to produce the expansion. If it's a positive number, it gives the value. And if you want to expand of this one, you write expand command here. Automatically it expands. See this one. We can also define a delay operator. So, if you want to substitute x value, some expression is there. I want to replace x by some numeric value. This is the value I will. This is the way I have to give. I'm clearing the x value because previously I assigned some value. Now I'm clearing. 2x plus 5 square, whole square means cap we have to give. 2 space is there means it understands that it is a multiplication. 2x plus 5 whole square. It is a cap. Power means cap. When I'm assigning, this is the operator I have to use. Slash dot x assign some value, some 3. So these are the simple syntaxes which we have to use. This is very much useful for those who are beginners of this software. They need to understand. Now, limits. This is a very powerful symbolic computation. Whatever the order of the value, the function, how complicated function, even though it is, it compute the limit value at any point very nicely. See, I'm clearing f first. I'm defining a function f of x underscore equal to x cube minus 1 by x minus 1. Limit of the function, the command is limit. Here, no need to write any other things. Limit means limit. L-I-M-I-T, L is capital, closed bracket. Argument has to be given within the closed brackets. Here, what is the argument? The function f of x approaches to 1. So the value is 3. Now I want to plot this f of x. See, the plot syntax is PLOT. P is capital, the function value, and x varying from where to where. It's in the curly braces. If more number of arguments are there, that we have to put in the curly braces in the Mathematica. So in the plot syntax, in the curly braces, x, comma, x varying where to where, minus 2 to 2. It gives you the plot directly. And also, left hand side limit also we can compute, right hand side limit also we can compute. See this one. F of f1 of x equal to 1 by x, limit f1 of x approaches to 0, infinity. I am giving the direction towards positive side. That means left to right. Left to right means it producing, when it is moving, when we are moving left to right. See this graph. When x is moving towards left to right, the value of the function is minus infinity. When the direction is negative side, means right to left. As x approaches to 0, the value of the function is positive infinity. So we can also do left side limits and right hand side limits. And also I plotted this one. Plot, the command is plot the function x varying where to where, -1 to 1. Next, another function I am considering, sin 5x by x. See, here there is a space in between 5 and x. Suppose if the space, if I remove, see 5 space I am giving x. Sin a trigonometric function divided by x. And also I define plot style. The plot color is red and thick. It produces the function f2, plots the f2 and the limit value is 5. See this one, as x approaches to 0, the limit value is 5, both side limits. And also we can define piecewise functions. The command is piecewise. See here the commands are user friendly. Only thing you have to see once the command and directly you can give. P is capital, piecewise, first argument x square plus x, when x is less than 0, we have to put in the curly braces because many number of arguments are there in any command. We have to represent in the curly braces. Here I am giving many arguments. So I am first representing all the arguments inside the curly braces, and within the first argument, as x less than 0, the value of the function is x square plus x. X lies between 0 to 3, the value of the function is 1 minus x. And x lies between this one, the value of the function is this one, x greater than, see this one. When limit x approaches to 3, what happens, and the plot also. So I asked the Mathematica to present the h of x value, the function. When x approaches to 3, here, the value of the function is -2. See this one in the graph. And I asked to plot this one with all ranges. Plot range is all. And as x approaches to infinity, what happens? Limit 1 plus a by x power x. X approaches to infinity. See, the command here infinity is infinity. See, this arrow we will get by putting minus sign and greater than symbol on the keyboard. Arrow means minus sign first, then greater than symbol. We will get the arrow. X approaches to infinitive. It produces the value. And I want to see the rational form of this function. What is this limit n into 2 power 1 by n minus 1. Sometimes what happens when I am giving typing this kind of commands, somewhere we may miss the syntax, actual form. If you want to see whether I give the correct command or not, you can see the traditional form like this. So this is the command I want to give. What is this limit value? Log 2. Limit n tends to infinity to n into 2 power 1 by n minus 1. See when I am giving this, asking the Mathematica to, as n approaches to infinity, what is the limit of this function? It is giving the direct outcome. Now I want to see what are the intermediate steps are there. See this one, how beautifully these things are working here. It is executing. When it is executing, this cell is in thick color. It is taking much time. A bit time. See this. All the intermediate steps of how we are evaluating this limit function. All the steps it produces. This is the beauty of Mathematica. I have never seen such beauty in any other tools. See, first I want to find this limit. To prepare the product, first for the solution by L-Hospital rule, write this one. Now I am applying the limit. Apply the L-Hospital rule. We will get all the intermediate steps, so step by step, very neatly. First we have to differentiate the numerator and the denominator, the differentiation value, and then the simplification value of this is the one, and then finally I will reach to this state, apply the product rule of the limit. See how beautifully, and use the fact that 2 power n is a continuous function of n and produces the value, and finally reciprocal rule of the limit, and limit n tends to n is infinitive, 1 by infinitive is 2 power 0. So finally we reach the answer. All these intermediate steps neatly, step by step, it is produced. See what I did. I asked the Mathematica, this is the command, one from alpha. Actually it is the tool, because that tool is not available directly with me. I mean, that's why I use this as a command. I'm asking the limit value as n goes to infinity. See, this is the what states means step by step with lines. I want to represent my step by step solution. That's why this is the command I have given. So it produces like this. This is the beauty of mathematics, symbolic, powerful symbolic computation. So next, I'm moving to the continuity and derivative and integration. Here also we'll see. I want to for the continuous functions within the interval there is no gaps and holes. So see the plots of different functions. See this plot style. I asked the color CMYK color. See, CMYK color means there are generally those who are working in Photoshop and these graphics, they know CMYK color and RGB colors. C means represents the cyan, M is magenta, yellow, and K is key means it is black. The combination of these colors, 4 colors, produces. Suppose first one is 0.82 and no magenta, and these combinations produces the green color. And RGB also, red, green, black. There are like this. Even we can give directly, suppose if I install this one, if I give green, it produces green but not that much thick color. That's why if you give based on that combinations, is always good. We can see this the combinations of the colors in Google also. CMYK color and RGB color also we can use. And also I also the thick lines. So discontinuous functions and discontinuous functions we can. So what I did, see, I am assigning each plot in the variable. First plot in the P1, second plot in P2, third plot in P3, fourth plot in P4. I asked the Mathematica to show all in one platform, one panel. How graphics grid means this is the grid, 4 grids I'm using. See, the graphic grids also we can represent like a vector. See, this is in the first row, first entry is P1. P1 means here one image plot. P2 is another entry. P3, P4. This is another first row vector, second row vector. Here the entries are graphics, plots. So this is the command we can use. So these two are the discontinuous graphs. I'm not spending much time over these things. I want to show the plotting of these continuous and discontinuous graphs, where the discontinuity is attaining, and we can see all these things. And the differentiation, when we see the function, derivative definition, through the definition, how can we do? Suppose the function is there, limit of the function, derivative definition is what? F of x plus h minus f of x divided by h as h approaches to 0. What is my function f of x? This is the function. See, it gives you the differentiation value of the thing. This is the differentiation definition. Through this also we can represent the derivative. Or directly we can also, the command is d, differentiation of the function with respect to x. It gives you the same. Suppose the 2 times the differentiation you want. So this is the x 2 times the derivative. This is the command we can use. 3 times the differentiation. So like this, we can ask the mathematical to differentiate function any times with the capabilities. So the command is d. D represent capital D, differentiation. With respect to what? How many times? Suppose if you give only x, one time it differentiate the function. So using the formula with the limit definition and general syntax of the mathematics, we can represent. See, this is the general different kind of syntaxes I have used. Derivative of the function, chain rule, product rule, together with the derivative of quotient rule, and the derivative of the function square root of e power 2x, exp. This is the function command representing the e power 2x plus e power minus 2x, square root of e power 2x plus e power minus 2x, differentiate with respect to x. This is the command. D, within the closed brackets, the argument of the function with respect to what. And also, in one go, I can see all the differentiation by using the map command. I am mapping this to the function d. Here, it takes the values of these arguments here in the hash, comma, with respect to x. And what is this? This is a vector. First argument takes here in this one sin x, cos x, tan x, arc sin x, and all the values. It produces. And I'm representing the plot of these functions. So what is my f of x function is this one, f dash f x. And also differentiation also, we can call the function like our general f dash of x. It gives the first order derivative. F double dash of x. It gives you the second order derivative. No need to give d of that function comma x comma 2 times the derivative. Directly we can give this also. I asked the mathematical to plot a tooltip mean within this all these functions. If I give within this command tooltip, when I place the cursor on the graph, see, this is my function f of x, f dash of x, f double dash, these things. So we can see what is the what is the function of this one. When you put your cursor on the curve, it represents the function value also. That is the tooltip. And also implicit differentiation. There is a function of two variable cos of e power x into y of x, and a y equal to, it is a function of x comma y minus x, differentiate with respect to x. Now I am asking to solve this for y dash of x, for the solution of this function. So this is the differentiation of this function, implicit function. So what I did, first I differentiate the function with respect to x. It produces some value. That value I assign to s1, and then we solve the result equation for dy by dx. What is the dy by dx? Dy by dx means y dash of x. So I asked the Mathematica to solve this function s1 equal to 0. Here double equal to represents the equality sign. Single equal to represents only assignment operator. If it is a single equal to, it is assignment operator. But here function s1 this equal to 0. I want to solve this for y dash of x because I need y dash of x value. Implicit differentiation. So this is the, like this we can directly get the value in one click. Now tangent lines. See, what is the tangent line? This is the tangent line. The f dash of a is interpreted to be the slope of the tangent to the graph y equal to f of x at the point a comma f of a. The equation of the tangent is given by this is the form, this one or this one. Y equal to f of a equal to f dash of a into x. This is the tangent. See, I am defining the function sin third of x comma 3 plus third is the one function. It is nothing but third of x comma 3 means x power 1 by 3. Cos x 4 power 1 by 3. I am asking the Mathematica to first order derivative of this function. So it is also this one. Now I want to evaluate this f of x function at the point with x coordinate x equal to 5 pi by 3. So my f dash of x is this one. I am replacing x by this value. It produces f dash of x. And y coordinate of the point is f of that point. Now I am evaluating the line, tangent line of the graph at the point x equal to 5 pi by 3. So y minus f of 5 pi by 3 equal to f dash of a into x minus a. So this is the graph. This is the tangent line at the point. See, what is this? How you can see? This is the function. At the point x equal to a, the tangent line what we are evaluating, that is at a different point. So suppose only this is the point at 5 pi by 3. I want to see why all these things, you know, mathematically we are evaluating everyday life, but historically how we can understand these things. Using the Mathematica, we can explain to the students and we can understand ourselves very neatly. See, I used P1, plot of the function. First, I used the plot of the function. This is the red color curve. Next, list plot means this is the data point plots. What is the data point? I want to plot this only dot data point. What is that? A comma f of a. See, what is slash n mean? The numeric value of this function it will consider. Plot style is something, and with the color this one. Next, P3 is another plot, which is the tangent line. See this. This is the tangent line. Y equal to, this is the function I kept here. From 0 to 4 pi, which is some color, plot style. Now I asked the Mathematica to show P1, P2 in one plot. Axis labels are x comma y. Aspect ratio means the look of the graph size. And plot range from -4 to 4. I asked. See, this is the function I got. Now, at different values of these points x equal to a, I want to see how this tangent line is moving over this curve. So I am using the command animate as it is all these P1, P2, P3s, previously what I used. Only I replace the point 5 pi by 3 by a because I want to vary this a value. Where to where I am varying, up to this one is same, the code, up to this one, this is the plot. which I have already previously given. P1, P2, P3, show P1, P2, P3 within this range. Now, I am asking to Mathematica, you vary the A value from 0.1 to 4 pi minus 0.1, 4 pi minus 0.1. And you first to see, put the point at 5, I asked that. See this, when I am running this animation, it is placed A value at 5. Then I am asking, when I run this one, it is showing how this tangent line is moving along this curve. This is the animation. This kind of representations are very much useful in interactive classes. While explaining the things in mathematics in the classroom like this, the students also get very much inspired by these animations. And also, tangent lines of parametric equations. Cycloid has been I consider the cycloid. See this one, same kind of things I'm doing. The tangent lines. First I consider x of t, y of t, differentiation. We have to get the derivative of dy by dx value, the slope, and second order derivative, derivative with respect to t of dy by dx, and simplify this one. It produces all these values. So x of t, y of t, x dash of t, y dash of t, and the derivative with respect to t. And then I ask the parametric, because these are the parametric plots, parametric equations. To plot these parametric equations, the command is parametric plot, x of t, y of t, t varies from minus 2 pi to 4 pi. Plot style, thickness and color I accept. And tangent plot, tangent line. This is the equation for tangent line. A value from minus 2 pi to 4 pi with scale 6 pi by 39. And it divides this minus 2 pi to 4 pi with this scale. The interval will be divided by this scale. And then P2 is another, I am evaluating two plot. What is the two plot? This is the one. The tabular values. It will consider as a table. Table means all the tabular values at from A running from this one to this one. A equal to minus 2 pi to 4 pi with the interval length, this one. It takes the tabular values. I asked the mathematical to plot this tabular value. The command is evaluate that table. All the values are kept in this two plot. And asking to show these two graphs. See this. At different A values. We have many tabular values. So this is a cycloid x equal to t sin t, y equal to 1 minus cos t graph at a different A values, above the tangents are there placed. While animating this one, you can see the animation of the tangent line along this cycloid. And orthogonal curves. See the contour plots. In order to get the orthogonal curves, we use contour plot. Command is contour plot. X varying from here minus 5 to 5, y varying from minus 5 to 5. Background shading I am not considering. Contour style thickness and all I have given. And second contour line. These two curves are orthogonal curves. When I plot these two orthogonal curves, we will get this kind of representation. These two lines are orthogonal. These two lines are orthogonal. Pictorially, we can see these orthogonal curves, how it is going, cutting one curve to another family of curves. And integrations. Come to the integration of any function, the command is integrate, regular word. Integrate the function. What is the function here? 1 by x square into e power 1 by x. Integrate with respect to x and derivative. It represents a direct integration. See, another function I am considering two functions. One is x square cos x, another one is x square into square root of 1 plus x square. This is the third one. I represented these three functions as a vector. Integrating with respect to x, it produces the value. And also we can map to many functions and produces the value. See, all these comments are very much useful while writing the programs in our research. Very, very, very important. See, another integrate sin x square, x from 0 to pi. What is the value? The output is pi by 2. See, the beauty of mathematics already I told you. If you want to see the intermediate steps, how it is, what are there? Suppose if you want to try to evaluate the integration of sin square x between x from 0 to pi. If you ask the Mathematica, see, integration 0 to pi sin x into sin x. You see the sin square x dx. The value is pi by 2. The numeric value is this one. If you want more digits, you can get the more digits by taking this one. If you hit this one, it gives you the step-by-step manner of intermediate steps. See, x, sin square of x can be represented like this, and integration, and then integrate the sum term by term, the factor out, and then cos 2x, the substitution method, how it is involved, each and everything. Even we don't give this much clear notes sometimes. Apply the fundamental theorem of calculus by evaluation, evaluate the antiderivative. See, all the things, all the intermediate steps, what are there to evaluate these things, it produces very neatly. And also, visual representation, very, very powerful. See, the Riemann sum, how it is calculated. See, I want to see all the cases of Riemann sum, not only left sum, right sum, and midpoint sum also. Here in this case, left sum is pi by 2 and right sum is pi by 2, midpoint sum also pi by 2. So the integration value, it converges to pi by 2. See, when I take the number of subintervals, here I consider the left sum. I want to see this one, left end point, mid end point, right end point. The Riemann sum we are evaluating, we can see with the left hand points. Suppose if I reduce the number of subintervals, suppose if the number of subintervals is 19, when it is reducing, increases number of subintervals, how these things are approaches to the curve. The convergence, how it is converging to the area is converging under the curve, you can easily understand. See, explaining Riemann sum by partitions and all these things mathematically, that algorithm is okay, but visually what is happening, we can show using these commands. Very powerful. Not only midpoint sum also. See, midpoint sum how it is. And the right hand points, if you consider, how the representation is there, we can visualize all the things. And also, sometimes when you ask the mathematical to integrate this one, see this. What is happening? Integration of e power exponential, exp means exponential e power minus x square into cos x cube. It is not a regular function. Between the limits 0 to pi by 2. It is not producing the analytical expression because of this. So I am asking the Mathematica to evaluate the numerical integration. The command is n integrate. Directly we will get the value between the area between 0 to pi by 2 under this. Next, power series. So I am clearing the p values and a values because I am using this one. I am representing the coefficient of the power series A. The inputs are x, x and k.
Hello. Hello.
Yeah. It is an into minus 1 power k divided by 2k plus 1 factorial x power 2k plus 1. P naught I am assigning to a of x comma 0 the value. Next Pn I am calculating by using this recurrence formula because it has to accumulate all the values n minus 1 to n. Now I am asking to the Mathematica to represent the power series expansion up to 2 second order, up to 10th order. It produces in one click all the values. And also the graphs. What I asked, first one is sin x. This is actually sin x representation of the power series. What I did is the sin x in Maclaurin series expansion. I have considered this one for simplicity to explain this one. Sin x graph. In the sin x first term, p x comma 1 and a first degree polynomial, third degree polynomial, fifth degree polynomial. Between the limits minus 2 pi to 2 pi. Remaining plot style different colors. I asked the for the representation. Tooltip means when I place this cursor here, it is a sin x graph. This is the P1, P3, P5. Power series up to degree 5. So these are the graphs we are getting. How these are converging? I will see with we can see with the animation. What I am doing, I am increasing the n value when n equal to 1. The graph of the power series at first order is this is the one, orange line. Actually, the sine function is this one, blue line, blue curve. When n increases to 1 to 8 with 1 step, see how it is converging to the curve. So every function we can represent, every continuous function we can represent in terms of the power series expansion. So how when it is increases to see at 8th degree, it is almost equating the sin x function, the polynomial within minus 2 pi to 2 pi. Suppose if you take 4 pi to 4 pi, suppose I consider up to 5 degree, what happens? 5 degree, 5th degree polynomial is not that much accurate. So when you increase the length of the interval, the degree of the polynomial must be how it is when it is converging. This phenomena state that at what value of n it is approximated to the original function, the polynomial. We can visualize very clearly. Now, suppose if I take up to 8, it is good agreement with this function. So these kind of visualizations we can see using the mathematical. And also a cos x representation series. We can also take directly cos x series function up to 14 degree. The command is series. It gives you the Maclaurin series expansion of the cos x directly. Whatever the function if you give, continuous function, it gives you the series expansion. So normal means I don't want to see this order. That's why we can see the normal. If you put, it represents the value and see the plot. When it is degree is 2, the graph how it is converges to the actual function. At the 64th degree, the power series Maclaurin series is coincides with the cos x graph within the interval from -5 pi to 5 pi. So this is the beauty of the mathematical. Now partial derivatives also we can perform. The derivative with respect to the function I have considered sine of square root of x square plus y square minus 5. Differentiate with respect to x the function, differentiate with respect to y, and differentiate first with respect to y and then with respect to x. Differentiate with respect to x first and with respect to y, both are same. And derivative 2 times partial derivative because it is independent variables are 2. So differentiate with respect to y 2 times together. And when you plot this function of several variables, 2 variables, we have to use the 3-dimensional plot, 3-dimensional plot. I'm not showing the time because due to the time, we have to run out of the time. See, the function is this one, plot 3D. I define the function. It is a function of 2 variables, f of x comma y, x varying from -2 to 2 and y varying from -2 to 3. Plot points 50, that means the mesh points. So these are the points which you consider x side, y side. See, function of one variable, it is a curve. The family of combination of curves in x direction and y direction produces surface. This is what. So I want to see the viewpoint in this direction. We can also see in a different viewpoints by changing the views, by putting on the cursor and representing it. So we can see the graph. And also we can produce the contour plot, stream plot, series. Contour plot, stream plot, and a combination of contour plot and stream plot. The vector notations, how the function is distributed in the y direction, and this is the stream function represented in contour plot. This is the stream function represented. Both we can represent in plot. We can combine these two graphs, the function of 2 variables. Come to the first order differential equations. We can easily, if it is a linear differential equation, this is say y dash of t minus y square of t into cos t equal to 0. We can solve this variable using the variable suburban method. In mathematical, the command is dsolve. D is capital, S is capital. The differential equation y dash of t minus y of t whole square into cos t equal to 0. For what? Y of t, the independent variable is t. This is the syntax we have to use. So it produces the y of t solution. So here C1 is the constant. Now, what is this solution one it produced? It is actually this is some kind of vectors. It shows different values. In the second argument of the first one, in the first variable y of t, you retrieve the solution. I ask the mathematical in that way. Now what I am doing, I am evaluating the tabular values using the command table. The solution for this solution, in this solution, I am substituting C1 by different values of these things between 2 to 10. And that means -2, -3, -4 up to 10. It evaluates all the possible solutions by replacing the C1 with these values, 2 to -2 to -10. See this, all the values. -2, -3, -4, minus already there, minus plus, up to 10 values. All tabular values. So it is within the curly braces, it is there, means it Mathematica understands this is a vector. This is the vector. I want to plot all these functions. See this. This is the first one, second one, third one, the family of curves. The solution of the differential equation is nothing but the family of curves at different constant values. We can see all this. The solution of the differential equation. And also, I am taking the non-homogeneous equation, first order. I am asking the Mathematica to solve this one. And the second equation. See, if the solution is correct or not, you can verify using the Mathematica. What I am doing, this is my solution. I am representing the solution as y1 of x as a function. I ask the Mathematica to simplify. Actually, what is my equation? Y dash of x plus c1 y of x equal to x square. I am substituting in this one. When it is satisfying, it gives you 2. That means the solution satisfying this equation. We can cross check whether the solution is correct or not. So in this way, this is the solution. We can also cross check. I am asking Mathematica to plot both in y1 and y2. So plot both the curves, both the solutions at a time. So within the plot, we can represent as a vector both the functions. Here in the function, x varying from 0 to 10, remaining are the different options of the function. I ask the Mathematica, frame is the true. And the frame label is this one, x, yn of x, different value y1, y2. And the legend, plot legends. What color one is the y1 of x and which color is the y2 of x? Plot legend also we can represent. See, here, this is the second system of equations we can solve using dsolve. So equations consisting, this is the system of equations. These are the initial values. We will get the solution. And also we can plot these solutions. So plot in the plotting, there are 2 solutions. And also I asked f of x plus g of x. Third solution. That's why we are seeing 3 different solutions here. And then second order differential equations. It will, all these are linear equations. This is a homogeneous linear second order equation with constant quotients, which will produce directly the value. Due to the non-linear equation, these all doesn't work. We have to go for the numerical solutions. So this is the plot of this solution. We can represent all the plots. This is assigned to in this solution, in the variable as a solution, t varying from where to where, plot style, all these things. Next, using variation of parameters method, how to solve using the Mathematica. Directly also we can solve the solution because it is linear equation. We can solve using this D-solve also, already I kept here. By using variation of parameters method. First, what I am considering, the corresponding homogeneous equation. The general solution is this one. These are the fundamental solutions, cos 3t and sin 3t. And Wronskian, I need to calculate. So first I define the solution, fundamental solutions, cos 3t, sin 3t as a vector. Now I am asking the Mathematica to represent this represent the first row, this represent the second row. So what is the first row? First row is Fs. Fs is what? Cos 3t, sin 3t. Second row is differentiation of these functions in order to evaluate the Wronskian. But when you see this thing, it is representing only in vector form only. I want to see in the matrix form. So command is matrix form. The variable, the vector, this is the vector variable, the variable matrix form or matrix form closed bracket variable, that also works. And I want to evaluate the determinant of the matrix. The command is the det of the matrix. Simplify. It simplifies the determinant value. Now, so the determinant is 3 here. Now I am integrating u1, u2. We have to calculate integration values. This divided by the Wronskian determinant with respect to t. u1, u2 I calculated, and particular solution will be u1 cos 3t plus u2 sin 3t. So this is my particular solution. Now, using the D-solve, also I am getting the same kind. So we can represent even the variation of parameters or homogeneous exact form, all the things we can do in mathematics. We can represent each and everything with text and all the things. So when you write the text, the cell you have to represent as a text cell. When you represent a code input, that must be the input cell. So when you execute this input cell, we will get the output. It is the output cell. See this one. This is the output cell. So like this, we can represent, and if you plot, you can get the plot of the solution y of t in the solution where it is. I assigned this differential solution in this SOL. So t varying from this one to this one and all these things. And also how to apply Laplace transformation method for initial value problems. So Laplace transformation already discussed previously. We use the Laplace transformation to transform one domain to another domain to the function. Previously it is in the time domain. When you apply the Laplace transformation, it is transformed to the parametric domain. Generally, we use these transformations and all for evaluating the signals to capture the frequencies. Here, we are transforming the functions time domain to frequency domain because for every a signal means generally it is mathematically a signal definition is a function of time. F of t is a signal. But if you plot f of t as it is, for example, this is a signal. If you plot this one, it is not giving any frequency information. So, in order to retrieve that frequency information from the raw signal, means the function which is in the time state, time domain, I have to transform the function to specific parametric domain, that is the frequency domain. So we use different transformation. We have in mathematics 2 kinds of these functions are there. We use operators and transformations. Differentiations and integrations are the, we say it is operators. Operator means it operates on the same domain. Suppose the function is in the time domain. If you differentiate that one, you will get the output also in the same domain, in the function of time only. But when you apply the transformations like Laplace, Fourier, and Henkel, and any other, when you apply this function, it's like a kind of function, it seems. When you apply this one, it transforms the function to one domain to another domain. This is in this one, how to apply this Laplace transformations in mathematics. We'll see the code. So this is my ordinary differential equation. Y double dash of the second order, non-homogeneous. External force term is the T into e power minus T, inhomogeneous term. And the initial conditions are y of 0 equal to 0, y dash of 0 equal to 1. Now, I'm asking the Mathematica to apply the Laplace transform. The command is the Laplace transform. L is capital, T is capital. No need to by heart the commands here. That is the advantage of the Mathematica. Differential equation for S domain. Already it is in the T domain. The differential equation in the T. Now I'm asking for in S domain. Transform to S domain. See, when you do that one, apply Laplace transformation, you will get y naught and y dash of 0, y of 0 and y dash of 0. So I asked the Mathematica to replace that values by, suppose if I don't have this one, if I execute, what happens? See this. Y naught of 0, y dash of 0 is there. Laplace of this function. And next this term is Laplace of t into e power minus t value is this one. Now I substitute the value in place of y of 0 and y dash of 0 by 0 and 1. It directly gives the particular values. Minus 1 and substitute the 0. Y of 0 equal to 0, y dash of 0 equal to 0. So it replaces. Now this is it is the Laplace transformation value with the input initial conditions is assigned in Laplace transformation ODE, LP ODE variable. Now what we have to do next? I am replacing it seems awkward Laplace transformation of this one. I want to see in our regular way y of s. When we apply Laplace transformation, f of t will be represented as a function of capital F in S. So I want to see capital Y of S. See this. The Laplace transformation will be in this variable function. The Laplace transformation is replaced by Y of S. So I will get this. I got this one. Now, in it is a function of Y of S. I am assigning this to another variable. Now what is there? I have to solve this equation for Y of S. So I am using solve for ys. Ys is a variable which is there, this function. I am solving for this for Y of S. In I am substituting that value in this function. I am assigning to this function Y solution of S. So now this is it is containing this function. Now I am applying the inverse Laplace transformation. So the command here is inverse Laplace transform. Inverse I is capital, Laplace L is capital, transform T is capital. This function. You can also replace this by this one, no problem. I have to get in terms of T. I have to come back to our original domain. So this is the solution. Now, what is this inverse ILT1 of T consisting? This solution. This is the solution of our actual initial value problem. Now I substitute the solution in this one. It has to satisfy. Okay, it is replaced all the y values with this function. What I am doing, I am asking the Mathematica to simplify this expression. So e power minus t into t equal to e power minus t into t. So it's satisfied. Right hand side, left hand side. forces are satisfied. So this is expression, entire expression. When you simplify this one, you will get this expression after substitution. So Mathematica as it is, it will produce the output as like this. Now I ask the Mathematica for me simplify this expression. The command is even, I see sometimes simplify also works. Simplify ODE check. If simplify doesn't work because of if there are many transcendental and other functions are there, trigonometric functions and exponential functions, we use full simplify. That works. And also, if it is inhomogeneous term or external forces are involved, unit step functions and impulse functions, we can apply the Laplace transformations, and also we produce good agreement of the solution. So different forces or external forces are given like these kind of things. Especially these Laplace transformation techniques we use for the applications of circuits. So actually, if you apply different kinds of impulse forces and unit step forces, and which is a combination of sine and cosine terms, impulses, sine impulse and cosine impulse, like that, if you give external forces in inhomogeneous, it produces the solution. I mean, also we will get the plot like this. All these are the steps which we already discussed. Inverse Laplace transformation I applied. After getting the inverse Laplace transformation, we will get some kind of expression. I ask the Mathematica to expand that expression and simplify it. Then the expression, the solution is assigned to x of t. Plot this one, the solution. So we can get the plot. So this is the commands we use. Laplace transformation we can apply, and obtaining solution we can plot. And also the same equation, this is the equation having Dirac delta function and unit step function. The Mathematica command is the Dirac delta of t, unit step function, unit step of t minus pi, x of 0 equal to 0, x dash of 0 equal to 0, also works, no problem. Because these are the linear equations, it works. See, this much lengthy expression I got for the solution. So if I ask the Mathematica to simplify this one, complex expand the solution of this one, which I assigned to SOL. It is a vector form, that's why I am asking the second variable of the SOL, first one. Complex expand I'm doing first, then simplify. So it produces a simple expression like this. So at a different values. Also we can plot this equation. And also PD is through separation of variables, which we already the theory which is there here. Professor Rajshekar sir already covered this one. I consider the displacement of the string wave equation, one-dimensional wave equation with initial and boundary conditions. The separation of variables, so this is u of t can be assuming like this, x of t into t of t, and solution, we will get the eigenvalue problems. We will solve that eigenvalue problems, and eigenvectors, these are the things. We will get the eigenvectors, xn of t and yn of t at a different eigenvalues. These are the eigenvalues. And the final solution is in the form u of x comma t equal to x of x into t of t. This is the thing, u of x and t of t with different summation n running from 1 to infinity. So an and bn's are the Fourier sine and Fourier sine series coefficients. These are the an and bn values. So using Mathematica, how to solve these equations and represent the graphs? First, I am defining f of x and g of x in the boundary condition. So my f of x is sin pi x, g of x is 3x plus 1. I'm executing this one. Next, we have to determine the coefficients an and bn in the series expansion of the solution u. These an and bn's we have to evaluate. These are the Fourier sine series coefficients. What is this? It involves integration with the period p 0 to p f of x sin n pi x by p dx. I am integrating here. The period is 1, 2 by 1, integrate f of x sin n pi x by p with respect to x between the limits 0 to p. P is 1. This is an. And I am asking the Mathematica full simplify an because it gives very lengthy expression. Simplify that one. Assumptions are the n values are integers. So actually the expression is sin n pi value is 0, so it simplifies that. Now I am also evaluating the bn. This is the expression. Yeah, 1 minute. Command I am changing. P of n. Yeah. So protected. Okay. So this is expression of bn. When we ask the Mathematica to simplify this one, we will get bn. Okay. Now the tabular forms. Why it is taking? I'm asking the Mathematica to tabular form n, bn with the numerical values, n running from 1 to 10, producing some bn, b of n. Okay. 1 minute, there is some bug in this command. It is this n shouldn't come. Actually, it is taking sometimes there is g of x integrate with respect to x. Okay, it is expecting the n value, the point of n. Okay. It is considered as n as the real. So that's why I'm asking this n as an integer. Okay, let us see what happens. It is there is some bug is coming because it won't protect n as a bracket. Okay, let's see. Now I'm evaluating the expression of Fourier series u approximate value cos pi t sin pi x. So it is producing the value when we put the values. These are the b1, b2, b3, all the numerical value, n value, n equal to 1, n equal to 2, all the values it is producing. Now, what I'm doing, I'm asking the Mathematica to up to 10th approximation. It produces in this way. Now, see, because of this bug, it is not showing all the graphs. There is some bug is there. Okay, it produces the command. Even the, if you animate this one, see this. This is the 10th approximation, up to 10th approximation of the code. I am plotting this code as the t varying from 0 to 2. When t varying from 0 to 2, the solution, how it is moving with respect to time. The wave equation. And also, you can use the dsolve command directly Mathematica without, if I apply dsolve command, it produces the solution. This is a D'Alembert solution it produces. If you use the dsolve command for this partial differential equation. So, this is the solution of one-dimensional wave equation in separation of variable method. We can do like this. And also we can visualize the solution when it is the time is varying, how this wave motion u is taking place with boundary conditions when I apply the forces like this, the forces. When you use this dsolve command, it produces the D'Alembert solution. So this is the power of Mathematica. We can, the graphical interface is very neat, very high computations also we can do, high programming also we can do. And also, the symbolic computations are very powerful in this Mathematica. We can use this in our regular classroom as well as in our research room. So with this, I hope I reached the time. I am actually extended even to that time. Okay, thank you very much. I over to you, the organizers.
Thank you, sir, for being with us and deliver excellent talk and share a lot of information in a short time with wonderful presentations on essential math fundamentals of Mathematica to differential equations. Thank you once again, sir.
Thank you, madam. Thank you very much.
Participants, please ask any questions.
Yeah, you can ask the questions. I mean, participants. Yeah, in the
Sir,
chat
so
box.
many participants ask, please share your PPTs.
Yeah, I will share my PPTs, no problem. I will give to you, you can circulate them.
Okay, sir.
I think every time clearing the variable,
Some of the
something.
participants asking how to apply software.
How to?
All these.
Yeah, it is directly what we say in the screen. Command line command line kind of programming this one. This is platform independent. We can use in any OS, but it is not free software. You go to the one from Mathematica, there is 15 days free license is there. You can download that one and you can practice that. That is a 15 days, some 1 month free period they are providing. Anything else, madam? Every time clearing variables is tedious. Anyway, to clear all the variables. How to export graphs to EPS? Yeah, every time clearing variables means if you don't clear when you are using the new program, it takes the previous values. You have to clear the variable. Otherwise, it won't. It replaces the previous values which you have given. So actually, when we are doing the programs, we use the different notebooks. So it is not a big problem when we are using one program for one notebook and another program for another notebook. It is not the problem because here I use only one notebook for all the things. That's why every time I am clearing I am using the clear command to clear the variable values. But if you are using different notebooks, no problem. And also, someone asked me how to import this to. You see, you just right click on the graph, save graph as. In that, many formats are available. PDF is there and EPS is there. Somebody asked me how to import, export as a EPS graph, GIF and GPG, any kind of format you can save this one. Clear? And any other?
Sir, another question. Can we apply this for RK method problems of numerical analysis?
Yeah, actually, this is a very powerful tool for especially numerical analysis. We can do all numerical computations in Mathematica, all computation, not only this one, even chemistry people also they can use this tool.
Okay,
all
sir.
numerical computations we can do. Because of the within 1 hour time, I can't present all the things. Numerical computations also we can do. Directly ND-solve algorithm, ND-solve command is there. It is a black box algorithm. What it is inside that ND-solve, how it is doing and all these things we can't see, but it produces the approximate values using some numerical techniques. Mostly it uses Rangekutta method. And also we can specify the method also. There are some methods are there. You can go through any material or help also. It is a very good, powerful help is there. If you type here ND-solve, capital N, D, it gives you a very good material.
Okay, sir.
Yeah, it
Next,
gives you
one
very
more
good
question,
material. You can go through this one. In Mathematica itself, very good help is there. You can solve all the nonlinear. It is a numerical calculations. It produces the interpolation function. It is interpolation function means it have. Suppose if you execute this one, I got this kind of interpolating function. These things. It won't gives you the explicit representations. This interpolating function consisting the numerical values of the solutions of this differential equation. This is a nonlinear differential equation because square terms are involved and cubic terms are involved in this one. So when you retrieve and plot the graph, we use evaluate the two functions x of t and y of t, because x of t consisting the numerical values of this thing and y of t consisting the numerical values of this solution, this system of solution, equation solution. So we can retrieve by using evaluate. This is the command, and whatever the thing you can do, whatever you can plot, you can animate, and everything you can. So any other? What about formula? Are they variable in the software or any separate book? What formula? What about formula mean? Yeah, books are there. Many books are there using for this Mathematica, but I suggest help is very good in this tool, in this Mathematica software. This help, no book is replaced with this help. I can say that one. Many number of examples are there. Different kinds of representations are there, options are there, everything is at one place. And also you can put whatever you have the doubt that you can put in the Google, or the Google also gives you some information. Using that one, you can modify your codes and everything. Which are the best for simulation? MATLAB, Mathematica, Maple. It is basically depends on the context of your problem. If it is the symbolic kind of calculations are there, I prefer Mathematica. Also, Maple also good. If it is good, I mean highly programming kind of and numerical kind of things are there. MATLAB is a good one. It is based on the problem you are doing. I'm using Mathematica and MATLAB both in my research because it's the basically if it is programming, it demands good heavy programming. I use MATLAB. If the symbolic computations and all these things are there, I use Mathematica. And any other R software is good. R is a statistical tool. Okay, for statistical computations, R is good. And also,
Thank you, sir. Clarifying the doubts.
Thank you very much, madam. Over to Prasad Rao garu.
Yes, sir. The time is less.
Yeah,
But the organizing report by PNV Prasad Rao garu, Associate Professor of our department.
Okay. Good afternoon to all. I am PNV Prasad Rao, Organizing Secretary to this national webinar and Associate Professor, Department of Mathematics. Today, Department of Mathematics, CRD Autonomous College conducted national webinar on mathematical applications on differential equations. Across India, more than 1,700 research scholars, faculty, students, and others are registered. This is the greatest achievement of the Department of Mathematics, CRD Autonomous College. More than 1,000 participants participated through Zoom meeting app and YouTube channel. I'm admirably thanks to eminent resource person, Professor GP Rajshekhar Garu, IIT Kharagpur. He is Dean and Planning Coordinator of IIT Kharagpur, and also he hails from Visakhapatnam. For his valuable address in mathematical applications in differential equations are made the national webinar as a grand success. And his explanation meets the more than our expectations. Professor Rajshekhar Garu covered the topics are analytical and semi-analytical methods to solve partial differential equations and PDF applications to lubrication process inside a human knee. This is a wonderful topic which the differential equations solve the medical problems, not only medical problems, it is a social problems and scientific problems also deals the differential equations. Very nice, sir. It was easy to understand, knowledge oriented and innovative. Once again, I thank you, Professor G. Rajshekhar Garu, for your valuable lecture. I also thanks to eminent and emeritus Professor Narla Vamsi Krishna Garu, Geetham School of Sciences, Geetham University, Hyderabad, and he is hails from Tenali, Guntur district. For his valuable explanation in MATLAB program of essential fundamentals of Mathematica to differential equations, real analysis, Laplace transforms, matrix, etc., it reaches our minds to explore the content is innovative and modern. His lecture was inspired us towards MATLAB applications in differential equations. Sir, you are the inspiration for us. Thank you, Professor Vamsi Krishna Garu, for your valuable lecture. Once again, thanks to both resource person, Professor GP Rajshekhar Garu and Professor N. Ramsi Krishna Garu. The national webinar has been made possible with the greatest support of our college managing committee. Okay. I am very much thankful to I am very much thankful to Dr. MBSV Prasad Garu, Secretary, CRD Education Institutions, for his precious support as patron of this national webinar. My sincere thanks to Dr. K.S. Vishmohan Garu, correspondent, CRD Autonomous College, for his encouragement and guidance. I am also thanks to Principal Dr. K.A. Ramraju for his ground level support to make this webinar as a grand success. I also thanks to Vice Principal Dr. K.A. Emmanuel, IKC Coordinator Dr. P. Paul Devakar Garu, Head of the Department B. Jagan Mohan Rao Garu, Faculty and Organizing Secretary also Srimati Hemalata Tinath, B. Srinivas Rao, Ram Brahman Garu, and Gupta, Faculty of the Department of the Mathematics and Faculty of the Computer Science, S. Kishore Garu, Swarup Garu, and Damodar Garu, and non-teaching staff of the college. I thanks one and all who were made the national webinar as a grand success. Thank you, thank you, thank you. Especially I thanks to the participants which made a grand success. Kindly fill the feedback forms. If they fill, they will get the certificates. Thank you, thank you, thank you, one and all.
Thank you, sir. Now, vote of thanks by Gupta.
Good afternoon, one and all. This is PNVS Gupta, faculty in Department of Mathematics, UG. Indeed, it's my pleasure to stand before you and give vote of thanks. Before it's too late, let me take pleasure to thank all dignitaries who participate in this webinar. I thank our eminent secretary, Dr. MBSV Prasad Garu, and our correspondent, Dr. K. Vishnumohan Garu, and Dr. K. Ramaraju Garu, our principal, and Dr. K. A. Emmanuel, vice principal of our college, and Dr. Paul Devakar Garu, IQAC coordinator, and also thank our resource persons, Dr. G.P. Rajashekar, Professor, Department of Mathematics, Dean, Planning and Coordinator, Indian Institute of Technology, Kharagpur, and Dr. N. Vamsi Krishna, Assistant Professor, Department of Mathematics, Geetham University, Hyderabad, and also thanks to organizers of UG and PG and technical section and office staff for giving us scope to conduct such a innovative talks using virtual platform, Zoom. So we have come to the end of the program. I therefore once again thank you all those who participated in this webinar and for making it grand success. Thank you one and all.
The session is end with the national anthem. The session is end with the national anthem.
जन गण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंधु गुजरात.
The session is end with
जनगणमन अधिनायक जय हे भारत भाग्य विधाता
The session is end with the session is end with the session is end with Thank you, one and all. The feedback form will send through WhatsApp and mails. Thank you.